Hi everybody and Happy New Year to all. I am Sharad Rai Chaudhary and I will be presenting fast online next best offers using deep learning. Me and my colleagues work for TCS Research. The agenda for today will include introductions and contributions, the design requirements, and the different interfaces that we have in our architecture, a feature storage structure, model building and optimization of the models, and technology stack choices and the different results. In today's world, data analytics has moved from descriptive and predictive to prescriptive analytics. What do I mean by prescriptive analytics is that what shall I do to involve customers in my B2C system by giving recommendations, offers, or running campaigns. But there is an inherent problem with this that the B2C system serves millions of customers per second. And also they have very low latency. So any recommendation system need to have low latency and high throughput. Also, we know that machine learning and deep learning algorithms works very well and gives good accuracy, but they need a very rich set of features to give good results. So our contribution is creating iPrescribe, which is a real-time high-performance streaming architecture for next best offers, and having a very low recommendation latency, which is 90th percentile of 38 milliseconds, and a scalable high throughput using open source big data technologies. And also we have done optimizations in the XGBoost implementation and the LSTM algorithm implementations. So these are the two models that we have used in our recommendation system. So what are the different requirements for creating such a recommendation system? So we have to create features from the data and train our models based on these features. Also in real time, these features need to get updated, and when there is a trigger for a prediction, these features need to be applied to the models to give the offers. So the different challenges for designing a high scale throughput and low latency architecture is that we have to have a very fast access to the stored features. And also we have to ensure that the throughput increases as the workload into the B2C system increases. Also, our model's inference time should be constant, and we have a layered architecture, but with a minimal communication delay between the architecture layers. So this is our architecture or the interfaces. So we have two types of interfaces. One is batch processing and another is real time. So the batch processing interface has the startup interface where it takes data from the persistent data store and creates features out of it and trains our machine learning and deep learning models. It stores the features in the in-memory data store while the models are stored in the model inference framework. In the real-time processing, there are two interfaces, the feature update interface, which takes each and every action of each and every user and updates the features correspondingly. And the recommend interface comes into action when there is a trigger for recommendation, and it takes out these features, create the input vectors for the models, and send it to the model inference framework for prediction. So the execution time for the startup interface would be T0, the time required for loading the data, and T2 is feature creation and model training time. And for feature update interface, we have the time required by the messaging layer, which is T3 and T1, and the T4, which is the feature update interface time, and also for the time required for communication in the in-memory data store. The recommend interface, in addition to this, also will have required the time to send the input vectors to the model inference framework, and also the offers that are generated by the model inference framework is sent through the messaging layer to the B2C system. But recommend interface and feature update interface being real-time interfaces, we need to calculate throughput for them too. So the throughput for recommend interface is defined as a minimum of two entities, the first entity being the number of cores required by the messaging layer divided by the time required for it, and the number of cores required for the inference layer divided by the time required for the inferencing module. And the feature update interface is the throughput for it is the number of cores required by the stream processing layer, which does the feature update, divided by the process time required for the feature update. So our feature storage structure, as you might have gotten a hold of, is done by two passes. The first pass is creating user profiles, which involve taking the data and creating a JSON type data format and storing aggregated features for each and every user, which are indexed on the user. So there are two kinds of features. We have temporal as well as non-temporal features. And when there is a trigger for prediction, we take these features for that user for whom we have to give the prediction and create concatenated one-hot vectors which are sent to the models for prediction. So we have tested our models on two data sets mostly, Recable and Instacart. So you can see the statistics for the two data sets. So we achieved the area under the curve accuracy for Recable to be 0.67 and F-score for Instacart of 0.3783. So we have used, as I have explained before, two models, a gradient boosting XGBoost model, in which we have used grid search to calculate the optimal parameter values, and LSTM deep neural network, where we have 150 node layer for Recable and a 20 node layer for Instacart, followed by 2 nodes of max layer for classification. And we have done a weighted ensemble of the probabilities given by these two models and to find out the final probabilities. So as you might know that LSTM deep neural network is very good. It gives very good accuracy on sequential data, which is the user's transactional history. But the big problem is that implementing it in real time is that when you want to give a prediction, you also have to give the entire user's transactional history along with it, which increases with time and also increases our latency. But if we unroll this, on the left you have this 1 unit of LSTM. So if we unroll it, we can see that there are only two vector values, C and H, C being the cell state and the H being the hidden state, which are passed between one time step to another. So what we have done is that we have taken out and cached this C and H values for each and every user in our in-memory data store. And during prediction, we take out these C and H values and take the current input to give the predictions. And the feature update interface updates these C and H values for each user as and when his interaction comes. Also I want to add that to achieve low latency for LSTM, we have implemented the LSTM in Java from scratch because the libraries that are available in Python gives a very high latency for inference also. So we have implemented it using JBLAS, which is a linear algebra library in Java. So the different technologies that we have used include Kafka as a messaging layer, which is horizontally scalable, and Ignite, which is a very powerful software from Apache, which is a stream distributed processing layer, and also it has Ignite Cache, which is used as an in-memory store. So we have also used Tornado as a Python web framework, which is primarily for the XGBoost prediction, which is still in Python, and a local list system as the persistent store layer. So below you can see the feature update interface in Ignite and the recommend interface in Ignite interacting with the Ignite cache to update and take out the features, and the Kafka and the WebSocket. So we have the Kafka sending the messages to these layers. So I will come to why I have mentioned WebSocket here. So the recommend interface again sending the inputs for the XGBoost model and the LSTM model prediction. So this LSTM is implemented inside the recommend interface of Ignite, and in the model inference we do the XGBoost model prediction, and we do the ensembling of the probability values of these two models. So Kafka, we have partitioned with multiple topics to support higher ingestion rate. However, performance gains with increase in number of partitions are limited by the disk access overheads. So we have hosted our XGBoost model in the web service of Tornado server, where we can have the facility of multiple processes listening to a port. But multiple processes listening to a port limits the throughput. So we have made that each process listening to different ports. Also, the XGBoost library spawns multiple threads which waits on the Python global interpreter lock, which again increases the latency. So we have set the OMP num thread, which is an environment variable, to 1. So each Python process will only spawn a single thread. And also we have attached each Tornado process to a single core by using the environment variable task set, so that there is no context switching and again no increase in latency. And Ignite, as I've said, we have used Ignite cache to store the features, the stream visitor to process each key value pair, and the stream visitor co-locates the processing locally on the node which contains the data required for processing. But the Ignite Kafka connector induces an overhead of 45 milliseconds, which is quite high. Therefore, we have also implemented a system using WebSockets, which are non-persistent, but yeah, it gives very good latency numbers. And also, we have launched multiple Ignite clients listening to different WebSockets. So our benchmark workload includes like the infrastructure of 6-node cluster, each with an Intel CPU of 56 cores, 256 GB RAM, and a 1 GB NIC. And we have trained our models on the training data of PAKDD and the Instacart data sets. The test data, what we did was we have taken it and extrapolated it, sorted it on clock time, and played it as a stream to emulate the user's action on the corresponding B2C system. And also we have controlled the ingestion rate to our system to measure the system throughput and the utilization. So these are the performance numbers. So in the top we have the startup interface execution time in minutes, time required for feature creation, training of the XGBoost and LSTM, and also the hidden states creation time for the LSTM model. In the below we have the recommendation latencies during in the real-time interface. So T4 giving the feature update times, and the rest mostly the recommended interface. T10 being the XGBoost prediction time. T7, which is the 14 millisecond, having the LSTM feature creation prediction as well as the XGBoost feature creation time. So we have tested our system by giving different workloads of 100, then 500, and then 1,000 messages per second. So as we can see that our system scales very well, and the throughput matches correctly with the workload that we are providing. But we can see that the recommendation latency remains the same across all the 3 different workloads. So below you can see the number of cores that has been used for each workload. The 100 being taking the 8 cores, 6 for Ignite and 2 for the Python XGBoost, and the 30 and 60 respectively. So our future work includes, one drawback of machine learning and deep learning models is that it needs ground truth. So it needs labeled data for learning the models. So our future work includes trying different methods, different tools where we can create the ground truth for the unlabeled data. So one of them is Snorkel, and we are working on it how to enable Snorkel to create labels for the unlabeled data. And also we are also working on different more deep learning neural networks. So you can ask why LSTM, why not CNN? So we are also working on using dilated CNNs, which is being worked on by our Delhi team, and we also need optimized implementations for them. So thank you. Any questions?
Hi, I have a few questions about the solution you built. First of all, how many users and how many products are you handling through this?
Okay, so as per our system, we have no upper bound for the number of users and the number of products. Our system can handle any number given the requisite amount of resources. That's the beauty of using big data technologies. So if you want specific statistics,
yeah. So the thing is, let's say you have 1 lakh users and 1 lakh items, which is very common for retailers, right? So in that case, how do you propose to scale up your system? Because the way it seems, especially let's say XGBoost, you would be actually calculating the scores for entire, that is 1 lakh cross 1 lakh. That's a huge number. So how are you handling that? And where are you storing it? And most of the recommendations would probably not even be used. So user choices always revolve around small pockets. So how do you handle that?
Yeah, so answering your first question, million cross million. So our XGBoost models are also parallelized using the Tornado web server, so that prediction for different products for different users. So at one point of time, we need to predict only for one user, right? So when there is a recommend trigger, a user logging in into the system, it will be giving recommendations to him. So we will be able to predict parallelly for different products for this user.
That's fine, but then for one user, for getting out the predictions, you will have to find out the results for all of the. So for 1 lakh products, you'll be predicting some values, right? Whether he'll buy it or not. But most of them would not even be used. And so just when a person logs in, how do you figure out? So
yeah, so this is on the onus of the person who will be using our system to provide a set of products predefined, which he will need to show to the user, so that we will be able to calculate the probabilities for them and rank them or whatever as the requirement.
I'd connect with you offline on this.
Sure.
Yeah.
So, thank you.
Thank you, everybody.
So, the second paper to be presented is on identifying multidimensional information from microblocks during epidemics. What is your name? It will be presented by Shalmali Ghosh.
Good morning, everyone. I am Shalmali Ghosh from IIT Kharagpur. This work, identifying multidimensional information from microblocks during epidemics, has been done in collaboration with Accenture Labs. So I'd like to thank all of them. So what is the motivation behind this work? Whenever there is some epidemic or outbreak, we have seen that there arises a lots of confusion about the situation, and people tries to learn actual information about the scenario. So in that case, in that situation, social media might be a source of information to people. So here we see that the Center for Disease Control and Prevention in USA, they uses social media to inform the American people about the Ebola outbreak, which was in Africa. So here we have collected some tweets. These are some sample tweets from the Ebola outbreak. We see that there are various important informations present in these tweets. So in the first tweet, we can see that someone has told about several symptoms of the Ebola outbreak. In the next one, someone tried to tell the prevention mechanism that one can take. So in the next few tweets, there are also several informations present. So looking at these tweets, we have come to the conclusion that there are these 5 kinds of tweets actually present in Twitter related to several outbreaks. So they are mainly the symptoms of the disease, prevention mechanisms, transmission, treatment procedures, and the death reports, casualties that are reported. Apart from this, there are a large number of non-disease tweets which not contribute to this disease awareness much. They are basically the sentiment of people towards the government and so. So who are the stakeholders of this work? So we would like to provide these three communities with some tool so that they can know instantly about various facets of an outbreak. So there is this pre-disease community who haven't yet suffered from the outbreak, but they might need to know the symptoms, prevention, transmission that are related to a certain outbreak. Then there are the post-disease community. They need to know the transmission and treatment policies that they should take or avail throughout the epidemic. Then there are also some monitoring agencies like WHO or some health officials who need to know how the disease transmitted to tell people, make people aware, also need to know the treatment that were done during that outbreak, and also they need to keep track of the death reports. So what is our broad objective? Our broad objective is to automatically classify the tweets into various informative categories. So there are prior works which have built some vocabulary-dependent classifiers to classify tweets into several categories. But what is the problem there? The problem is that for each epidemic, we have to build a different classifier based on the vocabulary of that epidemic. So the challenge is to develop a classifier which can capture features which remain same across various epidemics. So what is our observation? Our observation is that in Twitter, people follow certain traits in posting different kinds of tweets. Like each category of tweets, they have certain keywords which remains constant throughout all epidemics. So these features or signals need to be captured to develop the event-independent classifier. So for that, we have used a knowledge base called Unified Medical Language System and a tool associated with it called MetaMap. So basically, UMLS is a big meta thesaurus which contains over 3 million medical concepts, 133 semantic types, and 54 medical semantic relations. And the tool MetaMap converts a tweet or the words present in a tweet to some medical concept that are associated with it. If no medical concept is associated with a tweet, they don't convert it. They can't convert it. We have, this is our contribution, we have proposed a set of features. These features are generic, that is, they will remain constant for all kinds of epidemics. So there are 3 kinds of features. Firstly, the features extracted from UMLS using MetaMap. Using UMLS, we get features for the symptoms category and prevention category. There are this SOSY. SOSY is the abbreviation for signs or symptoms. This is one of the medical semantic types present in UMLS. And for preventive procedure, we have TOPP. There are also anatomical concepts which can be related to certain treatments or prevention mechanisms. The next set of features are the dictionary-based features. We have created our own dictionary which contains specific keywords for the transmission, treatment, death-related terms, and preventive terms categories. So if any of these terms are present in the tweet, so we can say that this tweet is of this category. Next are the lexical and syntactic features. We have considered presence of exclamation mark because exclamation mark is a kind of exaggeration. Those are mainly present in the non-disease tweets. And presence of question mark where people questions the several government policies and they also need to know several things. So they actually don't contribute anything to our classes. So for the data set, we have considered 3 data sets. The Ebola data set. Ebola is a virus that causes severe bleeding. It was outbroken in Africa, West Africa. Then there is the Middle East respiratory syndrome, took place in Saudi Arabia. And for dengue, we have considered dengue in India. So this is our data set. We have considered random sampling of 2000 tweets Three annotator annotated independently these tweets. We took majority verdict for determining the classes of tweets. And then we see that most of the tweets, like more than 80% of the tweets were of non-disease category. So it's really hard to gather sufficient data for the actual categories we want to focus. That's why we have considered 500 tweets from each disease, each outbreak. We have discarded the large number of non-disease tweets to maintain the class balance. So for the models, we have selected 4 classification models. The SVM with RBF kernel, SVM with linear kernel, logistic regression, and naive Bayes. We have applied this, both these proposed features and bag-of-words features differently on this trained our model using these 4 classifiers, and we have seen that SVM with RBF kernel performs better in case of proposed features, and logistic regression gives the best performance for unigrams, that is the bag-of-words features. So we have also trained a first text model with learning rate of 1 and 40 epochs. So we have performed in-domain classification and cross-domain classification. The blue marked digits are there, they are referring to the in-domain classification, and the others are the cross-domain accuracies. So I'd like to say that our aim was to build an event-independent classifier. So we have seen that our proposed features, they are giving far better results in case of cross-domain classification. That is, our objective is satisfied. The event-independent, our proposed features are performing far better than the bag-of-words feature. So the event-independent classifier we built performs better. But in case of in-domain scenario, clearly bag-of-words perform better because the models are trained on the vocabulary of the disease itself. So apart from this classification, we have also identified 2 pertinent problems, future works. So solving the problem of contradictory information presence in tweets. So we have seen that while annotating the tweets, we have seen that the various contradictory informations are present in the prevention and the symptoms category. Like some people says some prevention mechanisms and someone opposes that. So it is very challenging to automatically find the authenticity of a particular tweet. So that's why we need to develop some, we need to modify our classifier so that we can automatically find the authenticity of a tweet and serve people better. Next, we have also applied our classifier to a non-communicable disease called opioid. We trained our classifier with all the tweets from earlier datasets, and then we applied this classifier to predict the level for 76,000 tweets corresponding to opioid. We found that there was no tweet classified as death reports or disease transmission. We also took a random sample of 100 tweets for every other classes, and the human annotator checked and found that 4 to 6% of them were found correctly classified. So it is clearly noticed that information posted in online social media regarding a communicable disease like opioid, MARS, like Ebola, MARS, dengue, these are far different from non-communicable disease like opioid. So we need to find, in future we will like to focus what kind of informations are posted regarding these non-communicable diseases. So in conclusion, I'd like to say that extracting concepts, we have extracted concepts and distinguishing lexicons. So this helped to build a vocabulary independent classifier. These also satisfy the needs of the different stakeholders. And at last, we have also identified 2 practical research problems which need solution and which are very challenging.
Yeah. See, the proposed features that you have mentioned is all about UMLS lexicons, right?
It's about UMLS, it's about our dictionary, and it's about the presence of exclamation and question mark.
So you extracted the keyword list from UMLS and...
So we first do some pre-processing, standard pre-processing. We also see that when some kind of pronouns, sometimes they get mapped into various UMLS categories, but they are not important. So we removed those things and we took some kind of 4 things that I can tell you later. So we took those 4 kinds of post tags and we converted, mapped them using MetaMap.
But did you consider using Apache CTEX?
No, we didn't consider.
But because whatever you mentioned is all there as ready-made solutions in Apache CTEX.
Okay, I'll look into that.
Likewise, also since you are processing tweets, using regular post taggers might not work.
Sorry?
Using regular post taggers for tweets might not work.
No, we have used tweet-specific post tag.
And did you use, did those...
The arc tweet NLP, there is something.
No, but was that trained on medical words as well?
No, there is no medical Twitter post tag trained on medical data. So that things also need to be developed because...
Okay, so you said it is agnostic to the epidemic type, right?
Yes.
That's what you said, but the dictionaries that you are using are all basically medical dictionaries. And I don't understand why do you say it's agnostic?
Sorry?
Epidemic agnostic.
Yes, it is related to epidemics.
Maybe I'll follow up with you.
Okay.
How are you handling the cross domain? Means for the different diseases. Means for the dengue, we have the different domains. So, how are you using training on your own domain?
Here, cross domain refers to we are talking about different diseases. Like we train our model on Ebola, and we are testing it on MERS to see that the features that we have used for Ebola that also remains constant for MERS. So, in that case, our features performed better.
How do you handle domain-specific words in that case? Because you have a dictionary of your training data, and in testing data, there will be other domain words. So how do you handle that?
So we are showing that in case of epidemics, there are these generic features. So we are not taking into account the domain-specific words here. Domain-specific means what are you trying to say?
No, since you have some domain-specific dictionaries in which...
No, not domain-specific dictionaries. We have considered class-specific dictionaries. Like for treatment class, we have make one dictionary containing terms related to treatments. For prevention class, we have our dictionary of terms that contains prevention-related keywords.
So the keywords are not related to the disease, but
no, the keywords are not related to the disease. The keywords are
which remain constant across diseases.
Yes. So the keywords are related to these particular class-specific terms.
Okay.
So, have you tried for deep learning model?
No, actually the data set is very small and collecting larger data for this disease kind of things is very challenging because in Twitter, people mostly talks about government policies. They have some like casual talks. So the actual information present there is very less. So
can you try for like Wikipedia and other...
Wikipedia related to what?
Related to disease.
So we can look into that. So Wikipedia, the texts are mostly formal. But in Twitter, people are not talking into formal way. They are mainly using several abbreviations of several words. So I think some of the features will be different if we go into formal text from informal one.
Okay.
Yeah, thank you. So you have done a classification task, right?
Sorry?
Classification of 6 classes, right?
Yes.
So how did you handle this imbalanced data? Like for non-disease data, you have more samples.
So for data imbalance, the data was mostly imbalanced for the non-disease class. So
Yeah, so how
so
did
we have that I told that we have considered 500 tweets. So we have like if you see the data set, you will see that this number of tweets for the actual disease categories are quite compatible. So keeping compatibility with that, we have considered the number of non-disease tweets.
So now why can't you try like this, increase the number of non-disease data samples to 500 and do a hierarchical classification, like first classify whether it is whether the tweet is related to disease or not.
So you are talking about the relevance of the tweet related to disease.
Yeah,
Like
first figure out whether this is related to some disease or not, and then if it is related to some disease, then classify whether, what kind of disease, like whether it is symptom or prevention.
Yeah, so that will be a two-step process. So
Yeah, if you use this, then you can get more data in non-disease thing.
yes, but to make the gold standard, if we include them in the gold standard, we again need to manually check them about their correctness to whether they are actually, like there also a classifier is classifying the tweets saying that it is relevant to a disease or it is not relevant to a disease. So then again, we can't totally depend on a classifier to make our gold standard.
So maybe this interesting conversation we should talk later. Okay, so we'll move on to the next presentation. So this is so talk number 11, unsupervised multitask learning dialogue management, and it will be presented by Sushra, and co-author is Subhashish Sengupta.
Third presentation.
Good morning. Hope I'm audible to everybody. I'm Sushravya. So this is a joint work done with my ex-colleague actually, Subhashish Sengupta. I recently quit Accenture. So, and this work is done as a part of Conversational Agents group. So this is about unsupervised multitask learning dialogue management. So essentially, dialogue management is a problem where you look at the way in which the conversation is going. The agent tries to model the different directions in which it's going, the topic changes or intention changes or the emotional changes and things like that, and tries to adapt its response or some other kind of inferences based on that. So the main goal here is to model a agent, chatbot, or you could say in a place where we are trying to see the conversation, which is essentially problem solving to a very specific point that we are using it to debug problems like what you find in Ubuntu dialog corpus, where you have a problem and trying to debug a problem, software problems or other kind of problems. So yeah, so traditionally dialogue management used to be very done with using slot filling mechanisms. So you have a bunch of utterances and each of them have very specific slot values which are hand featured in the beginning of the task. But as you know, as every industry problem, this is not scalable at all because it's all hand featured. So that is why a lot of end-to-end sequence models have been trying to do dialogue management. So that there is no supervision or labels that have to be provided. Fortunately, it works very well for some cases like freestyle chats, but because conversations like goal-oriented problem solving or things like that are very, very specific and very dependent on how context is changing and things like that, such kind of models are, at least at present, don't work very well. After a turn to the problem or the utterance or the response doesn't become relevant anymore to the conversation. Okay, so the domain specificity is lost at that point of time. So like many papers have quoted experiments, trivial responses like me too, just based on statistical probability distributions that have been captured from the conversations in the dataset, just keeps saying irrelevant things. And domain switching is not at all captured there. So this was a typical problem because we have huge data in industry people, but we don't really have that much of labels. The thing is that we have things like mechanical Turk, but we really wanted to try out some kind of unsupervised way to do this. So we tried to explore what things possible there. So our nature at hand is to see if a goal-oriented conversational agent can do several things, like ask questions to clearly define user requests, or based on the requests, can it query knowledge bases and things like that, generate appropriate responses, inferring from different previous turns, and then also try to complete transaction to form a kind of knowledge tree based on whatever data set it's been having so far. So this is a typical example of CIO dialog transcript. So there's an in-house transcript. It's been delexicalized for privacy purpose. So saying hi, and I have some contract was created, but it was does not appear in serial or things like that. What should be done? So this agent says that he'll get back to you on that. So yeah, as we saw that our main agenda is to do it in an unsupervised way, and also at the same time capture meaningful domain-specific responses. So the one thing that we wanted to explore was, although we don't have much information about labels, we can definitely infer some kind of topics based on the utterances. What kind of topics have been talked about in the conversation. And we also found that there's at least a significant amount of data suggesting that topics actually relate to conceptual knowledge. And we thought that these topics can also see the flow of concept modeling in terms of how the conversation is going and where it's taking the intents and other responses. So this is in terms of, problem is in terms of debug assistance. So, explain. So just a few characteristics about data. So this is a CIO application that supports Accenture employees, essentially the in-house product. And usually it refers to many kinds of FAQs and databases that are there inside the system. And there's no label data whatsoever. It's just chat transcripts with different turns of utterances here and there. And so also, because if it's like very different to get subject matter experts for each and everything, so this is the unsupervised way we're taking. And couple of other things that we thought would help us sticking to extracting topics is because it doesn't like restrict the level of abstraction. So if you want to get a better, higher level extraction or lower extraction, you can adjust similarly the kind of concepts that you can capture. And also when it comes to extending to new domains, we don't have to get the entire model trained to it in a specific way again. You can also accommodate the new information and new topic related information and get going. And so we use our topic modeling for the specific categories of interpreting user queries, and also categorizing them into different action queries and for databases and responses, and to see what kind of strengths and weaknesses they have. So our problem statement as of now is like 2 steps: predict possible topics that have been talked about and generate corresponding responses which are topic relevant, which is the main thing. So this is the flow of the thing. So the first one relates to extraction of actions and intents and everything. The second one is to generate dialogue or do an action to the database or any such kind of API interaction and things like that. So as you can see, first process starts with delexicalization, extracting scriptgrams. We chose scriptgram because we thought certain kind of words can really capture the intent or the expressions of the and express the topics very well. So, and we obviously use like some kind of topic modeling, and we chose LDA for that. And then once we had this kind of LDA model, then we took each of the utterance in each dialogue transcripts, classified them into these kinds of different topics that were given out by LDA model. And then we used that in the next step. So next step is the 3-way challenge to classify what kind of utterance response has to be given in terms of each specific classified utterance that was given by the user. We'll come to that in a second. So the input model contains a large number of data sets, and so we have 3 important challenge models, that is bigrams, biscriptgrams, and bi and triscriptgrams. This is just what we tried with. You could also go with more. And so this is one typical domain related topics that we got from the data. So you can see that conversations about Salesforce.com, Accenture Salesforce, and things like that, approval pending and all belong to one kind of typical document. And later you can see some kind of greetings and okay, great or responses are kind of got into another topics. So this is topic-based classifications. And so we classified each and every utterance based on the topic it was closest to. And then we can see that kind of, what was the utterance, who said it, and what topic did it belong to. And so there was no dialogue information. And what we also tried to do was, because one of the reviewers also suggested that we also incorporate DAC information, that is dialogue information, we also tried, if not of unlabeled, if we don't have labeled data, we still can transfer the particular information from some freestyle domain which had this DAC information. We can just predict using that model. We tried doing that, and so we have this information, who said it, what kind of topic did it belong to, and what kind of DAC information. So we have some kind of labels now. So we tried to use a supervised learning model, essentially a joint learning model, for these 3 tasks, essentially. So the first one is intent modeling, depending on the user. Then second one is about system response modeling. And the third is system response modeling is response to the user. And the third one is system action modeling for itself, what it has to do within itself, like querying databases or accessing APIs and things like that. So for these 3 tasks, we try to do a joint modeling. And so that's the same. So this is just model details in terms of how we model the question and how problem statement and how we use the model. So we have a sequence of W0 to WT+1, which is essentially that words in that utterance. And C will be a system response. S is our system action. And this is joint kind of probability distribution modeling that we are doing here to predict the next step, the user response, system response, system action, and user intents at several places. And so data set, so this is the nature of the data set. We have human-human dialogues, and then we have around 6,300 dialogues as part of our training data, and test sequence consists of 1,400 dialogue sequences. And we clustered the model into 40 topics, and overall the vocabulary is around 280. And then we also, because this was an Accenture private data, we also, a reviewer suggested that we repeat the same thing on an open data. So we did it along for Ubuntu Dialog Corpus, and that had around, so Ubuntu Corpus has a lot of data, but we only restricted our topics to lengths of 35. And then we got around 2,300 transcripts, and test set was around 250 dialogues. Then we clustered into 200 topics, and vocabulary size was around 1,400 topics. So we got results for both of them. Training procedure, we'll discuss about results in a minute. So training procedure, so we use normal STM-RNN, and so the embedding size was 300, and mini batch size 16, Adam optimization was used, and dropout rate was 0.5. So all the details are in the paper. More details are also there, so that was all covered in the paper, essentially. And results, so we tried for both private data and open data. So fortunately, we got better results for the open data, which we can share out with you, and you can try it on the model. So the bigram clustering based model, which followed by the joint modeling, was around 27.4%. By skipgrams was 35.4%. Then the other one, pi and tri-skipgram clustering, and then using joint learning to find the response and actions and everything, was around 38.2%. Then we had done a repeated one, Ubuntu Dialog Corpus, and it got trigram clustering on 66.2% of accuracy, and 3,5 skipgrams, so 3 and 5 length skipgrams were used, and it gave around 73.5. So this is essentially the F1 score, essentially. So there are some references. Thank you.
So,
Hi, thanks for your talk. How you are identifying the title or the header of the topic? Are you doing manually?
No.
The second question is that if you are somebody asks the question which is not belongs to any of the topics which you have tried, I mean, he's asking something new concept, right? How are you dealing those?
So this is a completely unsupervised way. So we don't have any labels. So what we're doing is first topic clustering and then finding relevant clusters for each utterance in the dialogue. So if there is any new thing coming up, we can cluster it. We use the LDA, then it will belong to some cluster. Then we can assign that cluster to that particular utterance.
You doesn't need to label what you.
Yeah, that whole point is that we don't want labeling because it's like very mechanical and we don't want to do it because huge data set. So we try to use an unsupervised way in which we do LDA clustering over topics and try to get them. And from there we assign the clusters for each particular utterance in the dialogue and then use those as labels corresponding to do a joint learning for 3 tasks essentially. That is user intent modeling, system response and system action. System response is what the system is going to react to to the user, and what system action is what it's going to do internally within itself to find what kind of response it has to give, like query database access, or it can do some kind of API interaction or something like that to figure out what to bring to the user.
Yeah, my second question is that if somebody asks the question which is not belongs to any of the topic which is already you have.
Oh, okay. So this is not an interactive environment actually. It's like trained at once. So when you get the new data, you train the entire thing again or make the clusters again or something like that. Or you can also have separately cluster only the new data and then get topics from there and assign them to utterances.
So when you do the topic modeling, you just enumerated them as topic 1, 2, 3, 4, etc. And you said you have got 1400 topics, right? So is there a way to kind of label them like this is a sales contract as opposed to say support contract?
I think I would say the normal kind of abstraction that I would think of in terms of modeling abstraction, level of abstraction, I think what I could say is like vary the number of clusters. Like if you want very few clusters, I think we'll do a very high abstraction based clusters. You want to capture very small concepts or something, then probably more clusters is what I think.
No, my question was that that it's not because it's a bag of words. So how do you identify from the training data you have got a bag of words and the test data, how do you match them clear to it and give some kind of human based information, like like your chat was saying, it's a sales contract, I didn't include in that some document.
Correct.
Right? So how do you say that you should include it into the sales contract manual or whatever?
Oh, so talking more about active learning part of it, is
Yeah.
it? Okay. We haven't tried that. Maybe that will be a good direction, yes.
Hi, so I have a question. So usually what happens with email data is that most data is what you are not looking for. For example, hi, how are you? Yeah, I received your mail. We just spoke on the phone. So what happens is when you do the topic modeling, you are often left with a lot of noisy clusters and probably a few with technical terms. And this is especially true for a technical domain. So how do you get from there to mapping sequences? For example, when we are talking about, let's say, hey, my router is not working or this green light is not blinking, from there, how do you map things like, probably you should check if your LAN card is inserted properly. So that's a very deep level of thing that you need to do, and that's not possible to recover only from unsupervised models. I'm talking this because we have had a similar use case and we were stumped with these kind of things. So we could get out general responses, but when it came to technical domain, those things were very difficult to get out. So how did you handle that?
Absolutely. I think we also faced a lot of problems in terms of, we tried end-to-end sequence models.
So how did you do that again? Because you have very little data to model.
Correct. You have very little data. So at that time, platform deep learning won't work at all, is what I think.
Exactly.
So this basically has a lot of data. That is the main constraint here. We have a lot of data, and that is how we are able to do joint learning in the second step. So what I would say is, as you said, the topic relevance to maintain in the dialogue when you're generating it is very difficult. And exactly the whole point of it, why you're trying to model topics, is because if you do only sequence-to-sequence learning, but the second term or third term, as we observe, it will be like, I have this problem, X and Y, and the user response will be, I agree with you. doesn't make any sense, right? Because it's trying to model that kind of probability distribution from the data it has been learning. And if you look at Ubuntu dialog corpus also, there is a lot of noise in between what conversation is happening in terms of friendly chats, in terms of how the debate is happening.
But the problem with that is that in open general conversation, even if you say, how are you, even if I reply, I'm fine, it's fine. But when you're dealing with technical domain, you have to give the exact response. For example, you gave an example that there is some log problem, you have given an exact response, maybe you should check NBSP and something like that. So that level of knowledge from or building sequence of chats from simply supervised learning, that seems a bit ambitious. So if you could highlight on exact that technical conversation handling part, general parts are extractable,
Correct,
that's fine.
correct. So that's the exactly point I'm trying to make in this slide. Exactly the
Correct.
normal deep learning stuff, when you try a sequence learning, it's just giving some trivial examples.
Could you just come closer to the mic?
Sure.
Yeah, thank you.
So when we are trying to do normal sequence model, at every almost second or third turn, it will give some kind of very generic and trivial responses.
Correct.
So we didn't want to do just that. So the next step was for us to use topics, because topics indicate some sense of kind of direction or domain specificity for the conversation. So that is how we moved to domain-based or topic kind of modeling, and then using those things. So now what happens is now we're also capturing some kind of how the domain concepts are moving around in the conversation, and when you're trying to generate, you can also think about that and generate it. So what we, as a next step, we're going to use the normal end-to-end model, but also give topics as the other input, so that we can model both topics as well as a general kind of conversation, how it goes. So that is what we're trying to do.
So I didn't quite understand your evaluation metric. It seemed to be just matching responses in an existing corpus.
Sorry.
Your evaluation metric. It was just evaluating how well you match. I'm just wondering whether you've tried a real user study where you actually engage the system with a new user and measure like goal achievement and dialogue length, rather than just trying to match responses from an existing corpus. I think that evaluation for dialogue is very limited.
So the data set is the real data set. Essentially, it captures all the dialogues that have been happening for a long time in the CIO transcripts. So we've not done any kind of user studies as such, but we are trying to like jointly learn the labels for each utterance, essentially, that the topic clustering has given, and then use it for modeling dialogue response.
It'd just be interesting to see an actual evaluation with dialogues with new customers.
No, actually, we haven't done it with real people. These are just real transcripts, so we just stuck with. Maybe it should be.
Thank you.
Thank you. Thank you.
So the next presentation, talk ID 104, a hierarchical approach to skin lesion classification.
I hope I'm audible to everyone. Okay. So, good morning, I guess. Good morning to everyone. I'm Rahul, and this is Chinmay, and we represent Persistent Systems. And we're just going to be walking you through a small POC that we have done and some explorations that we have come across, so that we might lend and share our insights with you guys. So the topic again, sorry. The topic is obviously skin lesion classification. This came up as a POC from an American client, and he wanted some information regarding whether this was feasible or not. And he wanted to know the trade-offs of performance versus basically efficiency. Okay, so we'll be enumerating our work on three big broad steps. We'll tell you a bit about the challenge that it wasn't a POC, but the POC was coming to us by the client, but we decided to take part in this challenge so that we could show the feasibility of what he wanted us to do. So we'll show you what we did, and we'll give you some kind of takeaways that we thought were very important that would be good in commercial challenges. So just as a side note, this is not a very deployment specific talk, so this is not going to really consider a real-time production environment. This is going to be what we have done in deep learning, more or less. So some very simple statistics that you can peruse through. It's one of the biggest major skin problems, and obviously it is a very deadly type of skin cancer. However, it is pretty optimistic, so that if you have an early onset detection of this, you can actually have a survival rate which exceeds 95%. So that is very optimistic. So unless you aren't grossed out, please go through this. Sorry. So the challenge was essentially to classify an input image into one of 7 categories. The class distribution, as we'll show you, was extremely challenging for us because it wasn't consistent at all, and training a simple end-to-end classifier wasn't going to do the trick. So again, these skin lesions that you can see on the screen have different varying intensities and different severities. The first one, which is the nevus type of skin problem, is a simple nymph that you can get on your skin, and it majorly isn't really severe, but it can turn severe in very rare cases. It can turn severe, and that is why it is really important to make sure that we understand whether this is actually malignant or not. The other ones are, of course, again, all malignant, but they are different severities. So this is the class distribution that we have. Again, as you can see, NV is probably taking up almost 90%, or not 90, but almost 80% of the class distribution. Takes about 5,500 images out of the 10,000 images that we have gotten. This data set was obviously retrieved from the HAM 10,000 data set that we had, because we had obviously participated in this. Another side note to make is that we partook in this competition with only almost 1.5 weeks to go. So we didn't really have a lot of time to experiment. Okay. So class undersampling wasn't really an option because we couldn't throw away information about certain classes. We did remove some we manually did remove some images that we thought were not really important because the classifier was always misclassifying them. And we also thought of incorporating cost-sensitive training during the training phase so that we can penalize the classifier when it misclassified a minority class. So Chinmay will be going through our work.
When you are dealing with any kind of spatial data, the most obvious way to go is with a convolutional neural network. So that's our base architecture here, and we actually experimented with 4 form of architectures, and these are the common factors across all the architectures. So use of convolutional neural networks, then use of transfer learning. We took a pre-trained network trained on the ImageNet dataset, and we fine-tuned the weights to suit our dataset. And we used offline augmentation, not the online augmentation which many frameworks offer, just to save some training time. And this is the library we use for offline augmentation. It is an open source library and it's up on GitHub, so if you want you can go through it. Thanks. So this is the most straightforward approach you can always take when dealing with a classification problem, is just to use a pre-trained network. In our case, this was the Inception V3 architecture, and you just put some custom layers on top of it and you train it end to end. So so this is a multi-class classification problem, and as the previous slide denoted, the class imbalance was pretty heavy here. So generally the problem which occurs in such a case is that the parameter updates due to the minority classes is just too low, and the majority classes outweighs the minority class. So this is why this approach wasn't really an option. We just tried it to get a baseline of what the extent of the problem was. So to address this class imbalance, what we thought was maybe the classifier may be overfitting to minority classes, because the minority classes, that is these classes DF and VASC, these classes have very few images in them, around 1,000 and 100 and around 100. So what we thought was it may be overfitting to those. So we just took out some branches from the previous layers. So the parameters which are responsible for detecting these two classes will be were fewer than those required for detecting other classes. And we took out these branches considering the number of images in all these classes. So DF and VASC have the minimum number of classes, followed by AKIC and BCC, then MEL, BKL, and finally the majority class, which is the NV class. And we took out these branches and concatenated them at the end and trained this using the cross entropy loss with the softmax activation. But counterintuitively, it did not work out that well. So yeah, the intuition which applied to this problem here, the parameter update, which it is likely that this also applied here. So we haven't had the time to explore more on this, and we just moved on. So the next approach we tried to address the class imbalance was a hierarchical classification. So what we do is we split all these classes into multiple stages. We first detect whether it is an NV or it's not an NV. So this balances our distribution quite a bit, and it gives somewhat of a robust training. So actually, even for the hierarchical classifiers, there again comes a hyperparameter, which is the number of stages to use. So we tried with around 3 stages. I'm sorry, 2-stage classifier, a 3-stage classifier, and a 5-stage classifier. And we used a weighted cost function for training all these classifiers. This class weight, which you see here, is readily available in the scikit-learn library. And yeah, and I forgot to mention this, all these classifiers have been trained using Keras with the TensorFlow backend on a single GPU. So a 2-stage classifier first learns to detect whether it's an NV class, if an image is of an NV class or a non-NV, if it's not an NV. And all the images which are classified as not NV or others are passed down the pipeline, and we train a 6-class classifier again here to detect which class it is. Then the 3-stage classifier first detects if it's an NV or non-NV. Then if it's a non-NV, is it a MEL or BKL? And if it's neither of the two, is it one of these 4 classes? And then there's a 5-stage classifier, which, as you can see here, passes down images as this pipeline. So one thing we observed here was, even though DF and VASC had a very small number of images, they weren't really difficult to classify. So the scores for these 2 classes were much higher, almost up to 95 or something, 95% or something. So this is a design decision that came as to what to classify after NV and non-NV. So that's why we just take those out of the way first and then go down the pipeline. And the MEL and BKL, which you see at the bottom of the classifier, these 2 classes are the most hard to classify. The classifier isn't really. We tried a lot of architectures for this stage, for the MEL BKL, but as it turns out, it's particularly difficult to classify these classifiers, these classes. So yeah, Rahul.
So we'll be sharing our interim results with you as of now. The end-to-end 7-way classifier obtained a validation F1 score. So again, F1 score is we think it's the proper metric to be using here because accuracy will be very biased since you have a huge class imbalance. The end-to-end 7-way classifier gave us around a 0.76 F1 score. Those 2-stage hierarchical classifier gave us 87. The 3-stage surprisingly gave us a bit low, and the 5-stage gave us 93. However, there are certain things to note here. As Chinmay rightly said, the number of hierarchies that the hierarchical level that you go down to is again a hyperparameter, and the more number of classifiers the more number of individual classifiers you're making, the more number of overhead computationally you're making, which essentially means that you have to load 5 models into your memory at one time and then pass and cascade these inputs and their predictions one after the other. So this is obviously going to be sequential in nature, which means that if the second stage classifier classifies and some batch of images as not belonging to its hierarchy, it's going to pass them down sequentially. So again, performance-wise, the more number of classifiers you're going to make, the more accuracy, the more performance hit you're going to get. But it seems that making individual fine-grained classifiers seems to work well. So there is obviously pretty obvious trade-off between precision, accuracy that is, and your performance time on deployment environments. So just to give you a small, so all of these networks that you can see here were built on the Inception v3 architecture. We have tried a lot more deeper architectures again. So Inception v3 itself is a very deep architecture with at least 22.5 million parameters. And it has a size of around 220 MB on the hard disk. We went even across and tried the ResNet 50 architecture, which is around 27 million, then the ResNet 101 architecture, which contains another 20 million. So again, just to give you a, so Inception is pretty much the best trade-off, which gives you the bang for your buck. It has pretty good loading times and it generalizes very well across different data sets as well. So these were the online validation results that we got. The online validation, there was a portal that the ISIC challenge had actually given us, and we could submit our results there, but due to the lack of time, we could only upload 3 results that we could. All the 3 results that we gave us around 68% balanced accuracy, a 75% balanced accuracy, and 79% balanced accuracy. Interestingly enough, after the results were announced, we saw that the first position that was taken was obviously by the people who used huge ensembles. So ensembles with models which are 15, 16 models loaded into memory and then just taking a meta classifier which classifies their results. Early stopping doesn't really work. That's what we have seen in practice, because we generally have a lot of computation restrictions. So we can only train for a certain amount of time. We should generally try to avoid that or work around that using some way. We also found that in our experiments, stochastic gradient descent tends to generalize slower, but it tends to generalize better compared to Adam optimizers. And obviously, the more GPUs you have, the more better in deep learning. So the future scope, we'll just quickly go over the future scope. The first is obviously explainability in deep learning. We need to show the client what the deep learning classifier is looking at when it is trying to make its calls. You can't just give them a black box. So that is one thing that we are working on. The second is obviously, as I said, the first place was taken by a team who used neural architecture search. So this is kind of a meta architecture search which essentially searches for an architecture. It's an architecture for architectures. So they won the first place. The second is obviously better hyperparameter tuning and ensembles for each stage. That is, for each stage you have one classifier, an ensemble of classifiers. So that brings us to the end. Again, just as a side note, all our models and notebooks are posted on GitHub and they are completely open source, so you can visit the website and play along with them if you want to. Okay. Yeah. Sorry.
How is this hierarchy built? Like, is it directly built with the number of training set you have?
Yes. Sorry, I didn't quite get your question.
Like, how is the hierarchy of this tree built? Like, is it directly built with the number of training instances you have per class, or like?
Yes, it is built based on the number of classes that we had. So you're probably referring to these hierarchies, right?
Yeah.
Okay, so these were obviously made by using 2 decisions. One was obviously the class, the ease of classification of that class. So the easier the class was to classify, the higher up it was in the hierarchy. And the second was obviously how many examples of that class were present.
So you have trained like multiple things with multiple architecture.
So yes, again, this is not an end-to-end system. This is not going to essentially have a composite loss, and it's not going to train everything at one end. These are all separately trained classifiers which are joined together using a script.
Okay.
Thanks.
Hi, excuse me.
Oh, sorry.
Yeah, to add to his question, can you not use domain knowledge on top of it to build this entire architecture?
Yeah, definitely. If you have some EHR data which can give you some skin lesion information about the lesion, as in how malignant that skin lesion is, probably the diameter of the skin lesion, the color of the skin pigment, stuff like that, we might be able to influence the classifier to make better results. But again, it all depends, because we generally, again, the thing is, explainability in AI is pretty much the biggest trend right now. So we don't know what the deep learning classifier is going to look at. It might just exploit some kind of false bias in the EHR data as well. So we need to be very careful about that.
Sure. And another question. So, sure.
Okay, thanks.
So the last presentation in this session is the talk ID number 69, goal-based ontology creation for NLQ in SAP ERP platform. It will be presented by Jaideep.
Hi everyone, I'm Jaideep. I'm from IBM India Research Lab, and today I'm going to talk about goal-based ontology creation, which is specifically meant for natural language querying in SAP ERP platform. So before we actually dive into the details of the problem, we first try to let us first try to understand the background of it, so we can easily find the motivation of the problem. So to start with, what is actually natural language querying? So as the name suggests, in this setup, you have a backend data store stacked with your specific data. That may be relational data store which supports SQL query language, that may be ERP data loaded into a SAP system, and an end user who doesn't know about how to query the system using specific languages like SQL. So he or she will come and just post queries in natural language, and the onus is on the system to understand the query in terms of the domain and actually produce a executable query over the backend that can get executed over the backend and get the user the data back. So now to understand the domain better, so all this system typically make use of a domain ontology, which is made up of three main parts, which are like concepts, which are the set of entities which are participating in the domain. Then these entities, this class of entities will have some common features in them, which is the properties of that. And then there are relations, which defines how these entities are interacting with each other. So in a way, this is analogous to DB database schemas with tables, columns, and foreign key relations. And it is actually derivable from a database schema, but the only extension here is you can support much richer semantics in ontology. That's why it is typically much more preferred in natural language querying systems. Coming to it in a background of what are the works we have already done. So we already have a benchmark NLQ system. NLQ stands for Natural Language Querying. We call this system Athena, and we had a VLDB 2016 paper on it, which details about how the technology works. And then we had an industry track paper on FSC, which actually tells the tech transfer story of if you're trying to applying Athena on SAP ERP type of systems. And today's work is kind of a follow-up paper on the FSC paper itself, where we are trying to even dig deeper to handle more practical problems when you are trying to apply NLQ on SAP ERP. So coming to the SAP ERP snapshot kind of thing, so this ERP data, it is made up of multiple subdomains. So there is finance, accounting, there is manufacturing data, there is supply chain management data, and etc. Now, if I actually consider the whole database for this ERP data, and if I try to infer the ontology from this database, this is of humongous size, like concept properties relation, they almost scale up to some millions. And this much of scale is actually a problem, especially if you're trying to do natural language querying on top of this system. And why this is a problem, that we will be seeing in next few slides. So I have purposefully made a very brief overview of how NLQ technology works so that we understand where the problem exactly comes from. So I have taken an example of example question, which is show me list of users with SAP All Access. In this case, you can see that SAP All, this is a keyword that uniquely matches to one of the ontology elements. So the first step what NLQ tries to do is it scans through the question trying to figure out what are the different possible references of your domain elements has been made in the question. So SAP all finds a domain reference of UST04, which is this blue edge. Then there is a different word in the question users, which finds 3 different possible matches. So whenever you have these kind of words which can match into multiple different places in your domain ontology, this is typically a source of inherent ambiguity. You don't know for sure which of these matches were the actual intended one. So in such a case, as a second step, it tries to figure out the meaning of the complete sentence by combining the meanings of individual words. To do that, it actually considers the Cartesian product of it. And for each combination, the combination of meaning of individual words, we call it a selection set. So in this case, you can see there are 3 different selection sets which are being created because one of the token is matching in 3 different places, where the other token is basically a unique match. And after the selection set is created, the selection set is basically just a set of domain ontology elements, like a nodes in the graph. This can be disconnected also. But a SQL query or a backend query needs to connect all these nodes to find the intermediate join path. This is what we call as interpretation trees, and this is done by computing a Steiner tree on top of the whole ontology graph using these nodes of selection sets at the Steiner nodes. Those of you who are not familiar with Steiner tree, so this is just a minimal spanning tree, but instead of spanning the whole graph, this takes only a subset of the graph that it wants to span, and of course with minimal cost. Those subset of the graph is called Steiner nodes, and this particular computation problem is Steiner tree computation. Now, coming back to our NLQ on ERP, why this becomes challenging? For ERP data, as you can see in the table, there are quite a few like this. I have just listed the top ones. Like if you just consider simple words like status, it matches to 286 different places in your domain ontology. Things like description, it matches to 699 different places. Now, the problem is whenever you are trying to answer questions that involve such ambiguous terms, there is a combinatorial explosion of selection sets. This becomes evident in the examples I have chosen. So the question is like, what is the status and description of loans granted by Citibank? So this is specifically on the domain of loans. And then if we consider similar type of question in a different domain, like what is the status and description of orders placed by Dow Chemicals, which is more towards the orders and SCM side of data. In both of the cases, because there are ambiguous terms, status and description, you have selection set of the order of 10 to the power 5, which is huge. But out of all those, there is only one correct Steiner tree. That means only one combination of all those selection set is actually meaningful to answer the query. And that meaning also differs depending on what side of data you are in. If you are in loans, then status probably means what is the status of the loan commitment. Description probably means what is the description provided by the borrower while the borrower was applying for the loans. Similarly, if you are the different side of the data, like in order or SCM, supply chain management, then status means what is the status of this order with the shipment lines. So this is what motivates us to think that if we could understand what are the different user goals that are lying in this complete ERP system, what are the different set of segments of things that the user wants to query, then we could have probably created goal-oriented ontology to avoid this confusion completely, or at least partially, so that we do not end up creating so much of selection sets, and we will confine our interpretation only to the part of data where the user is interested in. And there also the major challenge will come from it's not just identifying the right subset of nodes, but you also need to identify right subset of intermediate nodes along with the edges, because as I just explained, the Steiner tree computation, it needs to identify correct intermediate nodes to come to the right join paths. So the challenge, this gives rise to the formal definition of the problem. So if we think the complete ontology graph to be G, and we have a set of goal tables, the tables that the user is interested in, or the set of such tables as T, what we are trying to do is we are trying to make a goal-oriented subgraph on the ontology G dash. So G dash, of course, will be consuming all the tables of T, but more importantly, the major condition here is The natural language querying engine should work correctly for any subset of T when working with G dash. So in a way, in a formal term, if I'm trying to define this, that means that whatever Steiner trees we can produce with any subset Ti of T dash using G, the complete graph, the same Steiner tree has to be preserved whenever we are considering the subgraph G dash also. And if we try to think of the complexity of the problem, it basically comes down to computing Steiner tree. It itself is an NP-hard problem, and then also the Steiner trees, computing Steiner tree of a smaller subgraph cannot be directly done from the computation of Steiner tree of a larger subgraph because it doesn't follow the optimal substructure property. So as this figure actually suggests, if you have computed the Steiner tree with Steiner nodes N1, N5 and N2, you cannot automatically infer what would be the Steiner tree for N1 and N2 because they are completely disjoint edges. So that basically means if you are really interested to compute the right Steiner trees for all the subsets, you have to enumerate all the subsets and compute Steiner tree for all of them, which makes this again an NP-hard problem. So we are basically trying to devise strategies based on heuristics, constraints, so that we can still approximate the problem without really actually enumerating all the sets. So the first strategy is more or less the structure-based, how the ontology structure is there. The idea is we first try to compute the Steiner tree for all the Steiner nodes, all the goal nodes that has been given. And then in that Steiner tree, we find the node which is having maximum degree. We just remove the node and all the associated edges with the node and again compute the Steiner tree. So the heuristics here is if you pick out the most influential node and remove it and again try to compute the Steiner tree. So it is forced to basically adjust itself to accommodate other important edges. So in that we hope that we will be actually accommodating all the important edges and nodes that we may need to answer all the subsets of Steiner trees. We keep on doing this until we are left with only one node, and all the while we keep accommodating the Steiner trees we are getting to the output graph. That's the strategy one, which is structure based. Second strategy is mainly built on some key observations, which is that in typical user query, it has always been seen that none of the user query typically contains more than some threshold number of concepts, like 4 or 5. So let's call it NC because we will be experimenting with different values of NC. And then there is another observation that typical user query don't span to different parts of the graph. So it is the farthest nodes in the right interpretation tree is within a threshold of a certain limit. Let's call it NR. So now instead of actually trying to retain all possible Steiner tree of all possible subsets, we are only interested in those subsets which actually obeys these following two observations or above two observations. So we first enumerate only those subsets. Those are within those bounds of NC and NR, and only for those subsets we keep on computing the Steiner tree and adding that to the output graph. And then there is a third strategy, which is lazy inclusion. The idea here is the main problem of this explosion of selection set is happening because there is inherent ambiguity in multiple tokens. In this case, if we could identify the context by seeing what are the other words which can uniquely identify some possible ontology elements, then you could have probably used that context up to figure out, okay, now I have context that this question is probably asking about loans versus the other question is asking about orders. Then I can actually figure out the ambiguous token probably should mean something very close to the unique matches that I have got. So this is the idea of lazy inclusion, that instead of creating selection sets with all the tokens at once, we will lazily include these ambiguous tokens only at the end of selection set creating, where we have identified what are the unique elements are matching towards. These are the three strategies, and we experiment with real-life end-user NL queries that is basically spanning over multiple segments of the data. There are 228 such questions which have been prepared by end users, and every user question is actually focusing on the group of tables the user is actually interested in. The metrics that we consider to evaluate our systems is on first is if the root cause of the problem is ambiguity. So how good we are in reducing the ambiguity if we are following the 3 strategies. Then 2 is accuracy. If we are actually creating goal-oriented ontologies, are we still able to answer the questions correctly? So we need to measure that how many of the questions are being answered correctly with the short ontology. And then there are optimization metrics like number of selection sets, time of computation, etc. The first set of results comes from if we are able to do the ambiguity resolution or not. As you can see in the initial slide, I had shown that in the complete ontology, there was duplications of the orders of, this was the range, 286 was minimum, 12298 was the maximum duplicates, meaning these are the ambiguity points. This has come down to 37, 37 is the minimum, 49 is the maximum for structured based algorithm, which was strategy 1. And for strategy 2, this is 36 to 46, which is much lesser, at least an order lesser than what it used to be in the complete ERP ontology, which actually also reflects in the number of selection sets being created. Now, average selection set creation is almost 3, which is the rightmost column of average, okay? So we are actually successful in resolving ambiguities, which was our initial aim. Now we must double check that we are also retaining accuracy. So in this case, the x-axis, this all pairs 2 numbers. These are the 2 parameters that we initially talked about. The NC, that is what is the number of concept we should be considering, and the other number is what is the farthest distance between the farthest nodes that we are considering for computing the subsets. As you can see, basically once we go on increasing the number, the right hand side of x-axis, time is always getting increased because we are considering more and more subsets and computing the Steiners trees for that. Whereas if you see the accuracy percentage, it almost reaches a peak in 3. So when both NC and NR values are 3, that means you are considering 3 concepts together, and the distance between farthest concept here is basically 3 edges. After that, there is also, although increase of time, but accuracy doesn't increase that much. So 89.42 is the kind of saturation accuracy we are reaching. Then the last thing is how many number of selection sets we are creating and what is the tentative time it is taking. So in case of non-lazy approach where we were enumerating all the possible selection sets, there was an average of 284.3 selection sets being created. Whereas with lazy approach, if we try to include the matchings at the last moment after we have find unique matches, this reduces to 3.32, which is a significant improvement. Selection generation time slightly increases, and it is expected because now I am making a decision that what is my nearest node when I will be including the lazy element, lazy token elements. And overall I3 generation time sees a rapid drop, which was the intended thing, because I3 is ultimately which is giving you the answer. So it drops down to 1.18 milliseconds from 143. So the summary here is our intention was to basically handle this practical challenge of scalability and ambiguity when you are dealing with such a vast scale ERP type of systems. To do that, we have proposed creation of goal-oriented ontologies, which will be much more focused on which user group is looking for what kind of tables and answers. And in doing that, we have proposed different strategies which can basically come up with right set of subset of tables and edges such that the correct Steiner trees and correct answers can be preserved, and all our experimental results are in agreement with that. Thank you.
Okay, thank you.
So the only source of ambiguity in your context is that you don't know what table they want to query. If they tell you what table they want to query, then everything else works.
So that is one potential source of ambiguity. Another source of ambiguity can happen if the same set of tables can be joined via different paths. So it is based on a work of Athena that I was just talking about. The ambiguity points are multiple. The main challenge that comes with ERP system is the ambiguity of identifying right set of tables. There are other ambiguous points which had been handled before. Like I was saying that even we have identified the right set of tables, but how to join them? There can be multiple possibilities to join them. There is a ranking algorithm there which takes care of how many edges you are traversing depending on it.
That's what you did before. In this
Correct.
work, you're handling the table identification.
Correct.
So since you're from IBM, I'm wondering how this connects to Watson. I mean, any comment on that you can make?
So yeah, NLQ. This is a technology piece that you call that we call NLQ, and it has been already available to some of the customers individually as a core piece, and I know some of the customers are actually using it. And for it being available as a product in Watson, I think we are already in discussion. There is already some progress that is on it, that is on testing phase and etc. But we can hope it will be in Watson in about a year or half a year.
Hi, thanks for the nice talk. So I have a couple of questions. One is very small. So the first, is the underlying graph connected?
The ontology graph?
Yes.
Depends on your database schema and how you have modeled your data. More often than not, it is a connected graph.
Because if it's disconnected, you would run into problems for the Steiner tree.
Correct. If it is disconnected, then if there is no join path between table 1 and table 2, you can't join it.
The second thing is connected to the first question here is there's still a gap between the Steiner tree gives you a joint disambiguation of concepts in the ontology, but there's a gap in the final query, right? That doesn't give you the query directly. So to understand that, do you use some expected answer types from the question? For example, am I looking for users or books or?
Right. So this goes back to the work of Athena. So basically it comes up with, there are different set of annotators that actually scans through the question. Yeah. One of the annotators is trying to annotate, is there any reference to the ontology element? Similarly, there are different annotators which are trying to figure out what are the particular select clauses that should be there? What are the things that the user is asking for? Okay. And depending on that, those things will go into the select clause versus whatever conditions you have made, that thing will go to where clause or having clause, things like that.
Okay, so query formulation is in Athena?
Yeah.
Okay, thanks.
There are a couple of more questions, but we'll take it offline. We already delayed the lunch. So thank you so much. And then the announcements.
Thanks for being here after a wonderful lunch. And I think we have some exciting talks here to keep you awake over the next 1.5 hours. So, and we have excellent set of speakers out here. And the first speaker, it is indeed my great pleasure to introduce Vivek Tyagi. So he's currently a manager at the Text AI team in LinkedIn, where his team is working towards developing novel word embeddings and deep learning classifiers to detect spam and low quality content from the LinkedIn feed. So before that, Vivek was a research director at Amex in Gurgaon, and even before that, he was at Xerox and IBM, and with working on different problems on speech recognition and speech analytics. And so he obtained his PhD from IIT Kanpur, so PhD from Swiss EPFL, and today he's going to talk about some high-performance convolutional neural networks for text classifiers. And I think we are all set. I think all the IT issues have been fixed, so we'll have a non-stop 90 minutes.
Sorry for the delay. There was a driver problem, I believe, in the Mac, which wasn't working well with the projector. Welcome to this talk. I'm a research manager at LinkedIn Bangalore. We work on text AI to remove spam, low quality content from the LinkedIn feed. So this topic is it's okay. We don't need that. Nechi, thank you. Not required. Thank you. So what I'll do in this talk is, unfortunately, I can't share a lot of details. So what I've done is I've actually done the experiments on the public domain data sets. We will provide you new insights that we have developed for convolutional neural networks, as the title says. And as the talk progresses, I'll share those details with you. And also some, results on public domain data sets. So these are watered down results, more to give you a flavor. And due to the confidentiality and so on, I can't share as much as I would like to. So please bear with that. Also, thanks to my team, a bunch of research engineers working on both the several production classifiers that operate on LinkedIn site in near real time, which keeps your LinkedIn feed, clean. And at the same time, they're also, investigating into these new techniques to further improve our precision recall results on our, data sets. So I'll start with a brief background. I mean, text classification is really a very old problem, right? I mean, 20, 30 years, and it's something which affects a lot of our, current web applications, social networking sites, Facebook, LinkedIn, Gmail, and so on. And flavors of the problem are to detect spam, low quality, profanity, harassment. These, by the way, are very important for LinkedIn. I mean, LinkedIn feed has to, there are terms of services of LinkedIn which requires the users to actually, post professional content which conforms with the LinkedIn terms of services. If people are, writing harassing messages, or if they're actually using profanity or hate speech, that is not allowed, and our classifiers actually act on those content and automatically take them out within real time. So that's the flavor of the applied stuff that happens. Also in other applications, large-scale text analytics is of interest for enterprise data to mine customer insights and, to do trending patterns, topics, and issues, and so on, which is not the application for LinkedIn, but in general remains an application for a lot of enterprise applications. Now, till 2014, linear SVMs, linear models were considered state-of-the-art for text classification. That's a known result, right? I mean, take lexical and gram features, throw them to linear classifiers, could be loss regression as well, linear SVMs, and they do a fairly good job. Things started to change 2014 around. LSTM, RNN, and CNN started to show good promise. And they have indeed shown good performance in the past 3 to 4 years. So that's a brief backdrop to the text classification area. Now, CNN, I mean, this paper, I think most of you are aware of, from Yin Kum, it came in 2014 in EMNLP, and he showed that the CNNs achieved state-of-the-art or better performance on several text classification tasks just out of the box. And he compared to RNN, LSTM, and a lot of what was considered at that time very powerful text classification techniques. He compared against them and showed that he gets improvement against each one of it. It's terrific work. That was the starting point for us, actually. So this work started about 8-9 months back. So we reviewed his paper, we looked into it, looked into the code, and so on. So what Kim did, he actually used the CNNs pretty much in a very good manner, but he pretty much took it as a modular box from the image recognition or image classification problems and applied it to text, which was great. But we believe, more rich architectures or more insights into how the CNN performs better as a test classifier can be had by digging deeper into that mechanism. And that's what we will present in this talk. One of the main insights for us was that when we started to analyze CNN at a very low level for our test classification, we started to realize that it's acting pretty much like match filtering. And match filtering is a very known and very strong concept in signal detection and radars, sensors, or other such applications. So it's a very classic results in filtering theory. And what we have done is start to apply it, at least in the interpretation sense, to the CNNs, and I'll share those insights with you in the next few slides. Also, please feel free to stop me if you have a question. We could keep it interactive that way. So, basic schema of how a CNN test classifier looks like. Most of you are aware of it. I'll just, maybe just for notational sense, I'll walk you through this. So pretty much what you're trying to do is, given a text, you fit it to a fixed number of tokens, fixed number of words, and which is the x-axis, and the y-axis is your embedding dimensionality. So the inputs are word-to-vec embeddings or glove embeddings, whatever you want to use. And you start with this 2D grid. So the tokens would appear on the x-axis, y-axis has the dimensions of your embeddings, and you're putting the convolution filters such that they span the entire dimensionality of the word vectors. So across y-axis, my filters will span all 300 dimensions. I'll come back to why is it so. And on the that is on the x-axis. So x-axis, you have 300 dimensions of the embeddings, and you will convolve with all of them. So your filter size of dimensionality 300. On y-axis, you have tokens. And there, as a designer, you have a choice what you would like to use as the filter width. And here, our hypothesis that for text classification, which is a classification problem, a discrete problem into C classes, given the grammar of the language and the syntax of the language, it's mostly few key phrases which carry the maximal sentiment in that document or in that sentence. And given the way the English grammar works and other natural language grammars too, most of the dependency is between 3 to 5 to 7 tokens. So you will have a verb phrase, noun phrase, verb phrase, object phrase, and adjectives all within the vicinity of each other. I wouldn't have a case that I have a token which is appearing at, let's say, position 10, and then there's a token which is appearing at position 20, which together form the discriminative pattern for the classification problem. That usually doesn't happen. It's localized within 1, 2, 3 to 7 tokens. With that strong prior knowledge, one would start by using the convolution filters of the width 1, 2, 3, 4, 5, 6. And in practice, indeed, that's what gave us the best results. So that's one prior structure of the problem that you're using, which helps to choose the design parameters. Now, in case of images, this is different, right? Your y-axis and x-axis could have very different filter widths. Typically, these are 3x3 filters. Because pixels, right? I mean, they have locality both across x and y axis. Reason we convolve across all 300 dimensions for the x-axis is because that entire vector makes one unit, because it's a word vector, right? I mean, so there isn't much sense to break it up into small pieces and then convolve it. Rest is, as usual, convolve with the filters. These are the activation values. The colored boxes, then you do max pool, stack them up, do a soft max. Now, as I earlier alluded to you, what was interesting for us was to start to build the match filtering interpretations into CNN. So the convolution filter is actually somewhat acting as a match filter. And I'll explain in a while what we mean by that. Let's briefly here review basic match filtering concepts. I mean, typically the way it is defined is that if you have a signal Sn, a known signal in noise, a match filter is a filter Hn which is being designed to maximize the signal to noise ratio of the signal of interest, which is Sn, and Vn is noise. So again, it's a very classic long-standing result. You could see the citation is 1960. And but it's one of the very classic results in filtering theory. What it says, the filter Hn which maximizes this is nothing but a time reverse copy of the signal itself. There's certain more specializations to it, which I'll let you read from the citation. But basically what it is saying is that if you geometrically look at it, forget the convolution operation, think of this as just a dot product. So dot product would be maximized when Hn is similar to Xn. Right? At the same time, this filter Hn also has to reject the noise Vn, right? Which is assumed to be which could be a noise with a given, correlation pattern. In a very simplified case, it could be white noise, but it could also be colored noise. In that case, you could still estimate your filter Hn such that it accepts as much of Sn as possible and rejects the noise Vn. One observation I like to add here is that while directly it is not possible to invoke this into CNNs because those are series of nonlinear transformations built into it, but locally if you look at the convolution operation, it is operating like this. Except that in this case, your signal Hn, signal of interest Xn, would be the most discriminative word vectors for your classification problem at hand, which you don't know. You will automatically find out. And actually, you don't, which we will show in the course of the talk. Actually, you don't even know what X and R. You're just going to throw your training data to it. But the dynamics is such that the convolution filters that would be learned, HNs, would be average representation of the word vectors which are most discriminative to the classification problem at hand that you're solving. And VNs could then be thought of as word vectors corresponding to the rest of the stuff, right? So there's a lot of redundancy in natural language. So all the determiners, stop words, articles, whatever, or even adjectives, which have nothing to do with that classification problem, would be treated as the noise by the convolution filter and would be rejected. So that's the dynamics that's happening in case of text classification. So again, some notation. I'll quickly step through this, but please feel free to stop me if you have a question. It's mostly for notational reason. Words W1 to WM map to word vectors, V1 to VM, filter QJ. You could use J filters, typically 200 to 300 are good. And filter size is K cross 300. So this I explained. We fixed 300. 300 is the embedding dimensionality. Don't play with that. Play with K. That has worked out the best, and that also is explained from the grammatical structure of the English language, other languages. Now, SI is the activation sequence after the convolution with a particular filter I, right? So I'm centering this at the token I, and we are looking at K activations, K convolution. So activation is the value that you get after convolution. So it's a sequence of length K. For simplicity, I'm centering this as token I, and there are K minus 2, floor of that to the left, K by 2 to the right. And this is what is, this was the sequences of the word vectors, and the convolution will operate on this subsequence. So Aij is the convolution of this subsequence Si with filter J. So it's going to look at the K tokens. And post that, you have the max pooling operation. Now, we hypothesize a couple of things here. And some of this I've already explained to you, but just quickly list them here. So whenever the activation Aij takes a high value, it implies Qj is acting as a match filter. Why match filter? Because that increases the energy of that output. So it's directly relatable to here. We're increasing the SNR, signal to noise ratio. So activation grows, whenever it's high, it means it's matching to that input. It's also worth emphasizing here that one could argue, well, the same thing is happening for lexical features, right? I mean, I could take n-grams and let the linear model, well, it sees all the n-grams in my trained data. So what's the big deal? It's looking at all the sequences. The point is that those classical lexical n-gram features, they quickly become high dimensional, right? And any ML classifier, even logical regression or linear models would still struggle with that high dimensionality. Whereas here, in a very succinct manner, what's happening is our filters are getting trained to respond maximally to only few of these, discriminative subsequences, which the SGD will automatically find out. We don't even have to tell it that, this sequence is what you should learn. Also, if you notice, what's happening is, unlike lexical features, because my inputs are embeddings, right? And to a large extent, you could assume that semantically similar words will tend to have similar word vectors. It's not exactly true, but approximately true. If that happens, then semantically similar lot of sequences will come into similar vector space, right? Because they're all close to each other. So if you plot them as vectors, they will tend to be similar. Once they're all similar, the same filter Qj, if it responds actively, maximally to one of them, it will also respond maximally to all those subsequences which are closer to H, right? Because it's just a dot product. That is where it becomes distinct from the linear models and lexical features. For lexical feature, if one n-gram tends to have a good weight in your linear model, a semantically similar n-gram wouldn't have. There's no guarantee for that. And it's becoming a very high dimensional space, and you're asking that poor linear model to learn that, well, learn all the semantically similar n-grams weights to be high. That's too much to ask, whereas you can accomplish that much more succinctly here with a CNN. So that's the match filtering insight into it. Now we get to the max pool stage. And this is where, it offers certain, you could say, advantages over classical sequential models in deep learning, such as RNN and LSTM. And I'll cover that in the next slide too. But if you notice, the max operation, what is it doing? It's returning the maximal activation value. So in a way, from that particular filter, J. So in a way, what it did, it encoded the memory in a very discontinuous manner, right? You could think of this as an attention as well, right? I mean, hierarchical attention networks, they became popular in text too. But this is a cheaper way to do attention, right? So this also explains some of the strength of the CNN-based text classification. The max operation achieves two things. One, it captures the maximum activation for you, which is the strongest evidence. Two, it is making that evidence position independent, right? So that maximal could have happened at any of the tokens. That doesn't change the classification label, right? I could pad some more tokens to the sentence, still I would get the same output. That's the strength of it, right? So these are the reasons why it generalizes better and so on. Please excuse this slide. I just put the LSTM equations just in case a question comes up that why does an LSTM performs better than CNN? It's a myth, actually, for classification at least. A lot of recent papers have started to show up that LSTMs, while they're very good at handling an arbitrary complex sequential learning task, but text classification is an overkill for them. Reason being that for text classification, most of your evidence is in few key phrases. You don't need a mechanism to continuously learn a memory cell state, right? You do have a mechanism for that, but you don't need it. The second aspect is that if we just invoke LSTM as a black box and put it on text classification problem, it works well, but not quite as well as a well-designed CNN. That's the argument we're making. Reason being that in case of CNN, you have a good control as a designer. What is the filter width that you want to use? So if you recall, we look up, coming from the grammar of the English language, we decided to use tokens of with 3, 4, 5, and so on, not 20. So that's the prior knowledge we use in a very simple way for CNN test classifier. Whereas in case of LSTM, you would have a continuous state, but it's kind of an overkill for that problem. And plus, you have no idea what is the extent of the tokens that are encoded in your memory cell, right? So some examples of these activations, the match filtering approach. So this is from the movie review data set. There's a first example, which is a positive label. Gosling provides an amazing performance that dwarfs everything else in the film. 71st filter started to act as a match filter for 2 trigrams. Provides an amazing performance that dwarfs. So that's the activation value. And the max pool will take the 0.25 value, store it as a evidence for the positive class. Negative example, again, it peaked for unpleasant excuse for. So just an example of the dynamics of how the CNN is providing that discriminative memory. I just have 2 minutes, so I'll quickly round up, give you some results too. These are on public domain data sets. Movie review, we compare against FastX, which is very good. But FastX still is a shallow network. It's fast from Facebook, great, but still it does not learn that discriminative sequence patterns that a CNN can. LSTM, okay, it's good, but yeah, a well-designed CNN would do better. Another data set on the AG news data set, again, significant performance from the CNN. Let me quickly summarize. So this talk provided more of flavor of how a CNN test classifier works by invoking the match filtering analogy, providing some connections to it. We show that a simple discriminative memory that a CNN learns is sufficient for test classification, and in fact it's better suited than other recurrent models such as RNLSTM and so on. Also, I'd like to acknowledge two of my colleagues who have done the internal peer review, Jeff Pasternak and Krishram Kentapati, and that concludes the talk.
Thank you. We have time for a couple of questions.
Hi, thanks for the talk. I have two questions. From where you are learning your word vectors? From your data corpus, or you are using the standard ones?
That's a good question. Actually, you could do both. If you have large corpus, learn it on your data. In our case, we glove and word2vec work reasonably well.
Okay, and the second question is, are you considering noisy text? Because in our domain, we are often dealing with noisy text.
Right.
Lots of errors.
Actually, that's also a very good question. I mean, I would say in that case, if you have a lot of data, then your first solution is a good approach to even train your embeddings on your domain data itself, which could be noisy, which could have spelling mistakes, for example.
And some words may be domain-specific words.
Right.
So in that case, you have to first identify noisy words and what are your domain words. Then how you are learning your class localizations.
See, what happens is, that's also a good question. I'll try to give you a short answer. What happens, we still incur a lot of out-of-vocabulary here. In those out-of-vocabulary words, we instantiate a random vector.
Okay.
So you don't have to be really perfect. You don't even have to have an embedding vector for every word. Even a random vector would do okay, because then your convolution filters will learn. It just needs a representation.
Okay, thank you.
Right, thanks.
So there's been a body of work on using rationales for text classification where users actually highlight parts of the document to show what part's important, and that's even been done on the movie review data, and it's been recently adapted. CNNs have been adapted for using rationales, and they seem to work better with CNNs than other techniques. Do you think your explanation connects in with that, and what's your feeling about rationales in CNNs?
Right. I'm sorry, I did not understand you mentioned there's another technique?
Rationales, you know what learning with rationales are, where humans have highlighted the parts of the document that most explain why they classified it a particular way.
I see.
And there's new results using CNNs with rationales, and they seem to help CNNs even more than SVMs or some other text classification. I'm wondering, I think your ideas are consistent with the fact that bias is consistent with rationales.
I see. Actually, that's a great point. A lot of pressure these days is also, as you know, is an explainability.
I'm talking about it tomorrow morning.
Right. So I don't have an answer, but I think, with activations, one could still start to bridge that gap towards why the CNN thought, this was a classification label for your text. So as we're showing those trigrams, right, that's like a cheap explanation for that classification label.
So next time we wait and
thank you.
Okay, so let's now get into the second talk. Next, we have Dr. Monojit Chaudhary from MSR India. So his research spans multiple areas of from AI, cognitive science, linguistics, and more particularly, he is working towards low-resource languages, code switching, and computational social linguistics and conversational AI. So he is also organizes the Panini Linguistic Olympiads for high school students and his high school kids, and he's also the founding chair for Asia Pacific Linguistic Olympiads. So he holds a BTech and PhD from IIT Kharagpur, and so today he's going to talk about processing code mixed languages. So let's give a round of applause for and welcome Manojit. Thanks.
Thank you, Bala, and I really want to thank the organizers for inviting me for this, because this is the first CODS I'm attending, and I'm absolutely loving the conference so far. And everything is perfect, the program, the food, and that reminds me, I mean, after such a good lunch, all of you might be, I mean, thanks to Vivek, he might have awakened up a little bit, but, you know, I want to give you a bigger jerk. So here are some 5-6 tweets that I have collected from Twitter. This comes from various parts of the world. It's shown where they are coming from. So you can see they are all in different languages. But what's common to these tweets? Can you figure out what's common to these tweets? Sorry for those in the back. You might not be able to see it properly, but at least those in the front. Yes? Many of these languages are written in this script. Any other guess? Not really. So this is Spanish, that's Turkish. So no, I mean, unless you know the languages, how can you say that? Yeah, so somebody said code mixing, I heard. So basically all these tweets are a mixture of more than one language. So for instance, the top one is a mixture of Turkish and German. The bottom one is actually very interesting mixture of French and Arabic. And people in northern Africa, the countries in the northern Africa, they do this kind of mixing of French and Arabic a lot, sometimes French, Arabic, and English, three-way mixing. And in India, we do mix all kinds of languages, right? So I don't have to really motivate you people that, you know, of the fact that people do mix languages. So this is a phenomenon which linguists call code mixing or code switching. I'll be using code mixing throughout the talk. And we have been studying this problem for last 5 years. We call it Project Melange. And this is with my collaborators in Microsoft Research, Kalika Bali and Sunena, and also with a lot of external collaborators like Professor Niloy Ganguly and Animesh Mukherjee from IIT Kharagpur, and Thomas Solorio from University of Houston, Alan Black from CMU. So this is a multi-group project, and we have been doing it for last 5 years. Now, before I get into what the problem statement is, I mean, what do you want to do with code-mixed tweets or code-mixed text? Let me give you a little bit of context. What happens in a multilingual society? So we all, I mean, assuming, all the Indians here, we all live in multilingual society. And a multilingual society means every person in the society speak more than one language, speak multiple languages, mostly the same set of languages, and all of them know this. So it's not that one person knows French, English, another person knows Spanish and Italian. That's not a multilingual society. So let's say Kolkata is a multilingual society because almost everybody knows Bengali. A lot of people know Hindi and English. So three-way mixing is pretty common in Kolkata. So what happens in multilingual society is, of course, we talked about code mixing or code switching. That happens. And it's interesting because linguists say in all multilingual society, they have observed this. It's a pretty common thing. But there are also other interesting things that happen. How do you decide, should I speak in Hindi or Bengali or English? You know, is it random? There must be some social choice that we are making every point we decide to talk in one and not the other. So this is an interesting question which linguists have studied. I will call it language preference. Then there's another interesting phenomenon that happens all the time. Think of when you meet a stranger in the roads of Kolkata or in this conference, what is the first language you start talking to that person in? Usually English because it's a formal setup. But then, would you continue speaking to that person in English, or would you eventually switch to, let's say, Hindi? Or maybe both of you know Telugu, so to Telugu. Who decides? What is the point when it happens? And it turns out there are subtle cues that the other person gives you that, oh, I'm actually interested to talk in Telugu. You pick up those hints and start talking back in the same language. So this is what linguists call accommodation. You are accommodating the choice of the other person. So there is this language choice accommodation that happens. So a lot of interesting things that happen. And 50% of the world's population is multilingual by various estimates. Now, all these are interesting, but very little NLP research has been done in it, in this area. Why I'm saying this is people do work on multilingual systems. But when they work on, when they say we are working on multilingual systems, they typically mean one of the two things. Either my system works for many languages, works across languages, or it means that my system is language agnostic. But usually they do not mean that my system can handle when people are switching between multiple languages. So, and imagine you are building a Cortana or any voice assistant for India and somebody asks, Cortana, aaj Kolkata ka weather kaisa hai? Is it raining or sunny hai? Something like this, right? So how do you, and this is very natural to any Indians. Or, a translator, speech-to-speech translator, which gets an input like that. And if you go to social media, we already saw tweets. I mean, if you are on Facebook, on Twitter, you know that people mix so much. So in Project Melange, we are trying to do two things here. So we are trying to understand the behavior of code mixing at two levels. So one is structural. What are the syntactic and semantic constraints on code mixing kind of thing? I mean, what kind of structures are valid and not valid? And also functional. Why people mix? What is the right point at which a person will switch? And those kind of questions. And eventually those things, when we understand them, they will probably help us, or indeed helps us to process mixed language better and build models that can tackle them. So this is the broad objective. Now, given that it's a 5 years research and I have probably only 25 minutes left, so I can't get into too much detail. So what I'm going to do is very briefly talk about three things. One is why do we care and why this problem is challenging, so the motivation part. And then very briefly, what are the strategies for solving it? I won't get deeper into the solution, but what are the strategies? So why do we care? I already said people code switch a lot, and linguists say 50% of the world is multilingual, so everybody would be switching. But that often turns out not to be a sufficient justification. So when we started this research, there were many questions. So one is, well, it's a peripheral phenomenon. Only, uneducated Indians do it because they don't know English well, so they mix other languages in English. Oh, I mean, if a person knows both English and Hindi, you make a English technology, it's fine. You make a Hindi technology, it's fine. People will, use the technology according to the language they know. So why you care about it? Or even we heard comments like, mixing is impure, and you should not use technology to, justify people to, or encourage people to make the language more impure. So I have answers to all those, and we have worked, 2-3 years rigorously to, give very solid reasons on why we should be using, solving this problem. I don't have time to go into that, but I will tell you two things. One is we have shown that code mixing is extremely prevalent all over the world, much more prevalent than you might have thought about. And second is code mixing actually provides a lot of very interesting linguistic and metalinguistic insight. So if you ignore it, you actually miss on those insights. So first, to solve the first problem, right? How much code mixing is there? So usually it's a speech phenomenon. People don't write in code mixing, so you won't find Wikipedia articles which are code mixed. But fortunately on social media, people write as they speak. So there is a lot of code mixing there. But still there is a measurement problem. The tweets, for instance, don't come up with a tag that, hey, I'm code mixed. So how do you know if they are code mixed? And the language detectors typically say, oh, it's English or Spanish, goes with the majority language. So we need a word level language detector. For every word in the tweet, let's say it says this is Hindi or this is English, this is Hindi, this is English. Bunch of interesting problems there. Actually, this problem of language identification at word level itself took 2 years of research, data creation, and all these other efforts to solve. But eventually, I'm not getting into those details, but eventually what we found are the following. So one is when we looked at India, so this is one study where we looked at public pages of Facebook, all threads were multilingual. So if you look at a thread as a unit, so there are posts, comments in the thread which are Hindi, there are comments which are English. All threads, sufficiently long threads were multilingual. And second is even within a comment or post, 17% were code mixed, which is a very large number, right? Then we looked at the world as at a large. So we built the similar language identification system for 8 languages. And 7, and the last one is code switching. And what's the distribution across the world? We studied some 50 million tweets coming from various cities. Turns out 3.5% of the tweets are code mixed, which is a sizable number given that we are looking at 50 million tweets whole world, although not as large as 17%. Some of the top pairs are like English, Spanish, English, French, and so on, but we also have, let's say, French, Spanish, or French, Portuguese, German, and Turkish kind of mixing. Then we did a city-wise analysis. It shows in which city around the world how much code mixing is there. So I would point out 2 things here. If you see Istanbul, which is on your right side, so Istanbul has the highest amount of code mixing. I think it had some close to 13 or 14%. And it was mixed between Turkish, Dutch, and English. Another interesting finding is there is a very strong inverse correlation between amount of code mixed tweets in a country, or in a city, with the fraction of English tweets. In the sense, more people tweet in English, less people code switch. So we took it to sociolinguists, and they had very interesting things to say about it. In one line, what they said is, in English-speaking geographies, people acculturize or very quickly with the culture. So if you go to America, you are an American. You forget your identities that you were an Indian, or at least don't try to project them. Whereas in Europe, actually, continental Europe, that happens less often. So this was one of the, it's not our finding. So when we presented this result, some sociolinguists interpreted the results in that way. So this is about the prevalence. So it's actually all over the world, happens a lot. The second thing I wanted to point is, the subtle cues that you will miss if you ignore code mixing. So there are a lot of theories of why people code switch, and I'm not getting there, but one of the theory is when you use your native language or mother tongue to express your emotions. Whereas you use a foreign language, let's say English, to express facts or other topical things, technical things and stuff like that. Sounds very reasonable, right? Assumption. So we thought we will test this hypothesis out on Twitter for Indian languages, English and Hindi. We collected tweets from bilinguals and did analysis, built a fact versus opinion classifier and all. Unfortunately, we didn't see any very interesting, things coming out. Then we thought, okay, let's not look at opinion, go deeper, look at positive opinion, negative opinion. So sentiment as well. And then immediately something very interesting came out. Hindi is preferred for expressing negative sentiment as much as 10 times more than English. So we wrote a paper that we might praise you in English, gali to Hindi mein hi denge. But interestingly, this pattern is male-dominant pattern. So most of the people in Twitter are also males. So therefore, it's actually very skewed towards that gender. But if you specifically take out the tweets from females and analyze them, you see the reverse pattern. Females, when they have to swear, first of all, they swear much, much less. But whenever they have to swear, they switch to English, actually. Because that sounds more sophisticated and, less, punchy, maybe. So the takeaway from this is if you are drawing inferences about what's the sentiment of people about, let's say, the coming elections in 2019, later in the year, and if you look at only English tweets, of course, majority of the tweets, 70% of the tweets from India are in English. But if you look at those and see a very positive sentiment for, say, political party X, but you don't know if there is how much negativity is there, because all the negativity might be in the Hindi tweets, right? So you have to check both the tweets, all the languages, if you want to get the clear picture of multilingual society. Now, this is at a macro level. Even in a conversation setup, it's very important whether the person is speaking in Hindi or English at what point. We did similar analysis for Bollywood movie scripts and showed how code mixing is very effectively used to, show who is coming back from West to India, who is trying to be bossy, or those kind of stereotypes. in the movie scripts. Okay, so assuming that this is a very important problem to solve, now the question is, why can't we just easily solve it? What's the problem? So there are, I would say, the challenges are mostly at 3 levels. So first is problem of data. Code mixing happens a lot on speech, but you don't have a large amount of text corpus in code mixing. Only recently, because of user-generated content on social media, we have some. But that's also not like enough. And they, as I said, they don't come up with the tag that this is code mix, right? So you have to specifically select the data. So there's problem of data. The second is model explosion. If you have n languages, potentially you have n square. Actually, even 3 languages can be mixed, right? But even if you don't go to those complicated scenarios, even if 2, so order of n square combinations. So do you want to build models, separately collect data, train models for each of these? So that's the second problem. So you don't want to do this. Third is more of a lost opportunity. If you build separate models for code switching, you are actually not utilizing all the monolingual data and models that we already have. And if you think of human beings, right, we are not learning to code switch as a separate capability. As soon as a person knows both the languages well enough, they can code switch. So we should be able to use the monolingual models. So let me come to the last part of the talk. Then how do you circumvent these challenges and how do you solve the problem? At the top level, you can think of, we could combine models, combine the models of language A and language B to build a model for AB. Or we could combine the data for language A and language B. Third is, could we also generate, since I'm saying there is not enough code mixed data around, could we generate artificially code mixed data? So we did experiments in all of these, and I will show what kind of model combinations are possible and which ones give the best results. And I will later talk about how to do synthetic data generation. So when you're combining models, one thing is you can build a fresh model from scratch, which would be like collect code mixed data and train a model. So you can think of a part of speech tagger or a translator as a model, like anything, whatever you fancy, a speech recognizer. The other technique that some of the people before us have tried is divide and conquer. So take this, let's say input, divide it into the 2 languages. So use a language identifier, divide it into 2 languages, and separately run the model 1 and model 2 in fragments, this side of the fragment and that side of the fragment. Problem here is often you miss context. And I will show you an example soon where each word is in different language. So A, B, A, B, A, B. So then you don't get any context at all. So this doesn't, actually this does not work well. The third one works better, which is you pass the entire, input through both L1 model and L2 model. You also pass the input through some other things, let's say language identifier, and where you could build your own customized other tools that you think are useful. Take the output of all these models as features and put it to what we call a combination logic or another machine learning system which is trained on this kind of features. And that also actually, that works better than divide and conquer model. But of course, there is a lot to improve on this. And the most recent ones, which work very well, are the zero-shot learning models. So surprisingly well, actually. So what you do is you don't do anything special. Train the model with L1 and L2 data as much as you have, but a single model. You use both L1 and L2 data in the single model. Just one trick you have to do, which is in every mini batch, you have to mix some data from L1 and some data from L2. If you don't do that, if you don't interleave them enough, the model gets biased towards the one which you train towards the end. And towards the end, to top it up, you train it with a little bit of code switch data. It's a very simple trick, but actually works pretty well. So let me come to now, then where do you get this code switch data? Can you actually have a lot of code switch data somehow? So this is a question which linguists have been asking for a pretty long time, which is, it's very well known that, not everything from, let's say, English and Hindi, you just mix a random bunch of words. They don't sound like natural code switching. So consider these 2 sentences, which are equivalent of the top sentence. Teacher has issued a book from the library for the student. So you can say, teacher ne library se student ke liye book issue ki. Almost like English, Hindi, English, Hindi, English, Hindi. Makes perfect sense, right? What about this one? Teacher ne library from student ke liye book has issued. But you see, I have almost retained the order of the words and everything like the previous one, but it's not working out well. Now why? What are the constraints, syntactic constraints on code switching? Linguists have proposed 3-4 different theories. One of the theory actually comes from Professor Arvind Joshi, with the late Professor Arvind Joshi, who has done a lot of foundational work in cognitive science. And I'm not getting into the theory, but what I will tell you is basically you start with a pair of sentences. So let's say we have this sentence, teacher has issued a book from the library for the student, and it's Hindi equivalent. Shikshak ne pustakalay se chhatra ke liye kitab, whatever the issue word is, liya. Okay. And then you align them. Now, once the words are aligned, now you pass the two sides. So pass both the English side and the Hindi side. Now, you can follow various grammatical formalism, that's fine. I mean, you can go with CFG kind of formalism or dependency formalisms. And then there are systematic ways of generating this code mix sentence, a bunch of code mix sentences from this combined structure. And different theories tell us what are the different constraints are. So for instance, in one theory, it says that if you have a non-terminal and you are expanding it, you have to expand either using the Hindi or using the English. So you are only allowed to switch in the tree once, but you cannot switch back again. So this is Arvind Joshi's theory. So if you come down, 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 if you have switched here from, let's say this is all English. If you see this one, this is all Spanish, sorry. If you go to that one, right, the last one, you can see that the NP at the end, right-hand side is a Spanish one, but everything else on the top in that path are English. So in a path, you have only one potential place where you switch. You can't switch multiple times. This is one theory. There are many other theories like that. So we implemented those theories. It's easy because we have translator, we can translate. We have aligners, we can align. We have parsers, so we can parse and apply those theories. And we generate. So typically, with a sentence of order, n words, you generate of the order of 2 power n potential words. Potential sentences. So it goes to like a 20-word sentence typically gives you 1,000 different versions, which are all valid code mix sentences. You sample from them, and you make a corpus of code mix sentences. So you just start with monolingual data and make a corpus of code switch sentences. Then we tried a various set of experiments, and we shown that this really helps. So one we tried was language modeling. So we showed that we can build language models, better language models for code switching, if we train the model in precisely this way. So first you generate the synthetic data and train with the synthetic data. Then you train with the monolingual data that you use to build the synthetic data. And then finally you use, if you have some real code mix data, then you use the real code mix data at the end. So this gives the best result. And by the way, we also tried mixing words randomly and giving it instead of the syntactic theories. That doesn't help. So the syntactic theories do have some value proposition here. Similar experiments we did for word embeddings, and there also we have shown that if we train word embeddings from code mixed data, even artificially generated, they are better able to solve code mix post tagging, code mix sentiment analysis, as opposed to if you were learning Hindi and English embedding separately and using bilingual or cross-lingual techniques to throw them in the same space. And it's actually easy to understand why. So synonyms in code mixed language does not retain the same distribution of its meanings as it is in the other language. So for instance, school in English has 2 meanings, school of fish versus school of kids, right? So school as a group, school as an educational institute. In English, school will always almost will mean school of children, educational institute. Nobody will say, when is fish ka school dekha. It would mean something else actually. It would mean it was in Finding Nemo kind of a movie, you did see a school of fish. So that's why, this cross-lingual technique doesn't work that well. So this kind of brings me to the end of the talk, which is, and I will summarize with the takeaways that, this many years of research has given us. So one is synthetic data seems to be very helpful, but all these techniques that I have told you are syntactic techniques. What happens is there are a lot of semantic and pragmatic constraints also on code switching, which we have not captured yet. So that's an open problem, because that will give you more natural looking data. Then I already said training curriculum, the order in which you train the models is very important. Third is zero-shot learning works very well in almost all these cases, and people will use it more and more, I'm sure, in the future. And finally, this is the most interesting open problem. So this is all about understanding code mixing. What about generating code mixing? If you want to build a bot which could code mix, what would happen? Now, that turns out to be a very hard problem, because it's not about just generating the code mix sentence. You have to know when to say it and when not to say it. To whom to say it. I mean, if I gave this talk in English, it would be totally, ridiculous, strange, right? A lot of people don't understand, and I won't do it. So a bot should know when to do it and when not to do it. And this is something which we are working on now. And that requires what I would say pragmatics, understanding social norms, identity, and things like that. So with that, thank you. And just for those who don't read Hindi, this is not that I lied in the talk. This is a Hindi word.
Thank you, Manoj. So we have time for a couple of questions. So.
Thank you so much for such an innovative talk. I have two questions. My first question is for when you were generating the code mixed sentences, how did you validate it if it is a correct one, or in the example that you gave, how was that validation done?
So that's a very good question. Actually, frankly, linguists, when came up with the theories, nobody did any experiment to validate. I mean, they did experiment, but those were like with 5-6 samples. So one of the studies that we did, we concluded the study only 3-4 months ago, we are writing it up, is we did a mechanical Turk study where we showed people sentences which are generated, and they had to mark them on validity, both real as well as generated. And we were trying to compare the models, the different constraints in the models and things like that. So we have some, nothing counterintuitive, I would say, but reasonable results, which says one of the theories, which is called the matrix embedding theory by Professor Joshi I was talking about. So gives the best kind of results for English-Spanish.
And my second question is more of an open-ended and future scope question. If I'm correct, tell me if I'm wrong. The languages that you used have the alphabets somewhat related to English. What if we are using languages like Russian or Chinese, which have substantially different symbols as well as pronunciations?
Yeah, so actually a lot of our work, and even this sentence, uses two languages which use two different scripts, right? But what I have used is transliterated Hindi in English. That's what most people do on social media. But this is a very geography-specific question. So when we looked at Chinese-English mixing in China, which seldom happens, only for technical terms they do it, they write the Chinese part in Chinese and English part in Roman script. But if you look at Chinese-English mixing in Singapore, they actually use all Roman script or all Chinese script, and they transliterate. So most of the geographies, when you are mixing two languages which use two different scripts, people would typically transliterate one of them. So the Arabic French, it did not use Arabic script, if you remember, it used the Roman script. And that's also pretty commonly done in Africa. So people select one of the script and just do it in that way.
So what is the size of the data you use for language modeling?
Okay, so let me try to recollect. So we could generate as much as code switch data as we wanted to, but I think because of the experiment time, we wanted to restrict it. So I think we did of the order of 100 million sentences or something.
Is it publicly available?
No, it's not. So we are working with a lot of people. So we are trying to make the code publicly available, the generator code. But right now, people who wanted to replicate our experiments, we ask them to give us the monolingual data, and we generate and give them back the data. We can't share the data because sharing tweets and sharing, other kinds of, we use the Bing translator data. So those we also don't have, I personally don't have right to share with
industrial
anybody.
track, so I think data sharing has its own implications.
Yeah.
So with that, let us thank
Thank you.
again. I request Manish to give away a token of appreciation. Thank you. Okay, so we have the final talk of this session is from Arijit. So Arijit is currently a senior machine learning scientist at the India machine learning team in Amazon, and his research interests are mainly in deep learning, machine learning, and computer vision. And prior to this, he was a research scientist at Xerox Research in India, and before that, he received his PhD in computer science from University of Maryland in 2014, where his PhD thesis was around semi-supervised and active learning methods with David Jacobs. So Arijit is also a recipient of the MIT Technology Review Innovators Under 35 Award from India in 2016. So today is going to talk about representation learning for e-commerce settings, and let's invite Arijit with a round of applause. Thanks.
Good afternoon, everyone. Today I'll be talking about semantic representation and analysis of e-commerce orders. So as you all know that e-commerce companies such as Amazon, Alibaba, Walmart, they typically process billions of orders every year. And it's very important to semantically represent and understand this order so that we can compute various kinds of similarities between orders. We can recommend the right set of products to right customers. We can forecast the demand of various products, etc. Now, what is an order? Throughout this talk by an order, I will refer to a tuple of customer, product, price, and date. So one such example is this, when Jeff Bezos purchases Whole Foods with the price tag of $13.7 billion on August 27, 2017. Obviously, our day-to-day orders are not as expensive as this one, but this just shows an example of an order tuple. In this particular talk, I will briefly go over two of our recent work. One where we create product embedding or product representation using a network called MRNet Product to Vec. And in the second part of this talk, I will explain generation of fake e-commerce orders using a generative adversarial network. So this work was done with Mukul, who is a master student at CMU now, and Shubhajit, who is sitting right there. So if we look at a product in an e-commerce company, you will see there are various components. There is the image which describes the product visually. There is a title which describes the product textually. So for most product, you will see that these two components are typically available in the website. But there are various other components also, such as the color, size, material, category, like the weight of the product, etc. They are typically entered by the seller who is listing the product in an e-commerce company. But a lot of times the sellers are a little impatient, or they do not have enough time to enter these details in an e-commerce website. So this information may not be available when you are looking for a product. Other than that, there are also information such as reviews or views or other kinds of customer feedback which you typically might have. But if a product is like a cold start product which has just been introduced into an e-commerce system, this kind of information may not be available. Hence, in this work, what we do, we take just the product title of the product and we feed it through a deep neural network and try to create representation which captures these various signals of products, or various characteristics of this product, such as size, material, the reviews or offers, or the target gender, etc. In this work, we didn't take the image of the product into account while creating the representation, but in future work, we could include that also. So what is the motivation? So any company such as Amazon or any Walmart, they have billions of products in their inventory. And obviously, as you know, there will be hundreds of machine learning problems that involve products. For example, product recommendation, duplicate product detection, product safety classification, price estimation, etc. And any ML application obviously needs a good set of features. Without good set of features, it's very hard to build ML models. Now, what is a good and useful featureization for products? So a very naive featureization could be a bag of words based representation where we could take the title of the product or other textual metadata of the product and create a TF-IDF based representation. Although this representation is quite effective and has worked well on various kinds of machine learning problems, they typically have large high dimension. So they tend to overfit. They're typically computational and storage inefficient. They are not semantically meaningful. That means they do not know that a computer and a television is much more similar than a computer and a shoe. And obviously these kinds of features increase the parameters in downstream machine learning algorithms. On the other hand, any dense and low dimensional features could alleviate all these issues. So in this work, we propose a novel product representation approach, which is dense, which is low dimension, and which is also generic, so that it can work well or it can be useful in a large set of or wide variety of machine learning problems. And we want to try to demonstrate empirically that these features are as good as TF-IDF representation. We train a discriminative multitask neural network where each task corresponded to one of the signals, and we incorporate various signals pertaining to a product, as I mentioned earlier. Some of these signals are static, such as like color, material, weight, size, category, etc. Some of these signals are also dynamic, such as price, popularity, views, etc. And as I mentioned earlier, that the learned representation should be as generic as possible. We refer to this network as a multitask recurrent neural network. Now, if you look at, if we quickly see the past work in this domain, in this representation learning, there are works like word2vec, where we create a semantic representation of words. Then there are a lot of work on like paragraph2vec or doc2vec, which creates representation of large or longer pieces of text. There were a couple of past works on product representations also, such as prod2vec and metaprod2vec, but these embeddings were particularly designed for the problem of product recommendation. We have seen that traditionally people have used multitask learning in the context of correlated tasks. When one of the tasks doesn't have enough training data, then we use other correlated tasks which have larger training data and try to use that information to improve your learning. But in our case, we use multitask learning to make the product representation generic. So we didn't have a scarcity of data. We didn't resort to multitask learning because of lack of data. We resort to multitask learning so that we can incorporate defined signals corresponding to a product to its learned representation. Okay? So these are some of the signals which we incorporated. Some of them are static and dynamic, and some of these correspond to classification problems such as color, size, etc. Some of them regression problems, which are real targets, and some of them are decoding problems. And if we look at the network, this is the network which we finally used to train our embedding. So we have the title, the words in the title of a product. We feed that through a bidirectional LSTM and create an embedding, the product embedding at the final time step. During training time, this embedding is fed to multiple task units, like some of them are classification, as I mentioned here, some of them are regression, and some of them are decoding. And this network is trained in an joint manner with all of the tasks together. So while training, we optimize this loss, which is the sum of the classification losses, the regression losses, and the decoding loss. This loss can be optimized in two ways. One is the joint optimization technique, where at each iteration we compute the gradient of the whole loss and update all the weights in the network. And another method which people commonly use these days is alternating optimization technique, where at each iteration you randomly choose one of the task loss, and backpropagation is performed with respect to only that loss. And only the weights of that task and all the task invariant layers are updated, but all the other layers are not updated at that particular iteration. So in the long run, we almost approximate the same loss as this. Okay? We optimize for the same loss as this one. And we could have used both, but for some feasibility issues or some implementation advantages, we used alternative optimization for this particular work. So once we created this representation, we applied it on various machine learning problems within Amazon. I'm not going to the details of the problems, and there are some results, but I will mostly focus on the qualitative results. So at the left row, you can see these are some of the products which we queried for from our catalog, and the right towards the right, these are the nearest neighbors we got. So you can see that here this is like a table horseshoe shaped and of gray color, and we find similar kinds of tables here. Here is a bed, and we find similar kinds of beds. Again, here is a toolbox, and the nearest neighbors are basically defined kinds of toolboxes. So that shows that we have been able to capture the product representation quite well, and it captures various aspects such as the color and the shape also here, etc. So that's some of the qualitative results. So as you know that Amazon works on multiple marketplaces or multiple countries in the world, and it's very important for us to know when a product is uploaded in India if that product is already available in another marketplace such as France. So we need to compare products across different languages. So that's why we extended this work using a multimodal autoencoder, which can transform the embedding of a product in one language to another language, so that we can seamlessly compare products across different marketplaces. And these are some additional results corresponding to that. In the left, we have looked for some products from the French marketplace, and we looked for their nearest neighbors in the United Kingdom marketplace. We found these were the nearest neighbors. You can see the query was a shower curtain, and nearest neighbors are also shower curtain. And similarly for bulbs and pillow cover, we got reasonable good results. For this part, we didn't do a lot of quantitative evaluation, but these results at least show that we're able to learn some of the important characteristics in the product representation. So now, next I will move on to the next part of our talk, which is a generative adversarial network for generating fake e-commerce orders. This was again work done with Ashutosh, who is a PhD student at Indian Institute of Science now and was an intern with us last year, and Shubhajit. So the motivation is again sort of similar. Amazon has billions of products in its inventory, and but the space of products is of much lower dimension. So because there is some inherent underlying structure imposed by the product categories, subcategories, price, etc. Okay, so all products can be represented in a lower dimension space. Similarly, although there are hundreds of millions of customers can also be represented in a lower dimensional space because there is some structure imposed by the behavior, their price sensitivity or brand sensitivity, etc. Now, an e-commerce order is a sort of interaction between these two spaces, and out of these interactions, only a subset of the interactions are ever plausible. For example, if a person who likes jazz music is very unlikely to ever purchase a heavy metal album. Or similarly, a Bengali is very unlikely to ever purchase a non-fish item. Okay? And even a smaller subset of these plausible orders are ever actualized on Amazon. So if you look at the set relationship, this is what it looks like. The set of actual orders is a subset of the set of plausible orders, and that is even a subset of the all orders in the space. Now in this work, we basically explored the space of plausible orders. Okay, that was our goal, and the reason was that we want to estimate the demands of products better. We want to estimate the customer preferences. We want to estimate prices better and seasonal variation of various products. And to do that, we propose a generative adversarial network called e-commerce GAN. So the key contributions in this part were threefold. The first one was creating a low dimension representation of e-commerce orders, which is called order to vec. And a part of it I already described in the first part of the talk, which is like product to vec. This is like taking everything into account and create a low dimension representation. Then we propose a conditional GAN to generate future orders condition on a product. So whenever a new product is launched in e-commerce, we do not know what are the kinds of customers who are going to buy these, when it is going to sell more. So using that GAN, we're trying to forecast that. Basically, that was our idea. And we designed several qualitative and quantitative approaches to evaluate the order generators. And if we recollect an order that has various components, such as the product, customer, the price, and the date, the product representation is basically, it's a simple representation. It's just the titles, the words in the title of the product. We take their word-to-vec representation and do a weighted average. For the customer representation, we take the past purchases and try to capture signals such as what is their preferences to which product groups they typically like, what is their price sensitivity, and how frequently they typically purchase. And using a multitask learning network, we learn customer embeddings. I'm not going to the details of all of these things. Price is just a 1D scalar, which is basically log transformed and normalized version of the actual price. And in the date, we created a 7-dimensional vector where we captured various days of a week, such that Monday, Tuesday, etc., various days of a month, such that first, second, third, fourth, etc., and various months within a year, such as January, February, etc. We carefully crafted these features so that the circularity of days or months are captured. And eventually concatenate all of the above to represent each order as a 264-dimensional vector. Okay? Now, the order to vec part is done. Now, a lot of you might be familiar with generative adversarial networks already, but I'll just quickly give an overview of generative adversarial network. It has typically two components. One is a generator, another is a discriminator. The generator typically takes a random noise vector and tries to generate samples which are very similar to a given set of true data points. On the other hand, the discriminator tries to discriminate between the generated data points and the true data points. And while doing that, the generator and discriminator involves in a competition sort of between each other, and the generator ends up learning to generate like samples which are very similar to the real data samples. Although, as you might know, that this GAN has shown very good performance in several problems like image generation and etc., there are still a lot of problem about convergence. It takes a lot of time to get good results or get a stable GAN. That's why and there are reasons for that. If you look at a generative adversarial network, when the discriminator has been already optimized or it is pretty good, it has reached its optimal state, it basically optimizes for the Jensen-Shannon divergence. And if you look at the Jensen-Shannon divergence, you will figure out that when the discriminator is too good and the generator is close to the discriminator, then it propagates the gradients well. The generator can learn from those back-propagated gradients. But when the discriminator is very good and the generator is too bad, then it reaches a vanishing gradient state and the back-propagated gradients don't have enough information for the generator to learn from. Okay? So that's the problem with Jensen-Shannon divergence. Hence, in this paper, the authors Arjovsky proposed a variation of the traditional GAN, which is called Wasserstein GAN, where instead of this Jensen-Shannon divergence, they use earth movers distance, which basically optimal mass transport based distance measure. And this, they found that it has a smoother gradient everywhere, so it is much easier to optimize. So the authors used that and showed that it performed really well. So we tried using Wasserstein GAN initially, but Wasserstein GAN also have some problems that the critique or the discriminator in Wasserstein GAN that needs to follow some constraints such as one Lipschutz or so, and then to resolve that there was another paper which was proposed last year by Gulrazani about improved Wasserstein GAN. So eventually we used that for our problem. Yeah, but this really helped in convergence, in at least in our problem, this really helped in good performance. Now, if you look at the network, it's very similar to the traditional GAN. You have a noise vector, you feed it through the generator, but since we are proposing a conditional GAN, or we want to generate orders conditioned on a particular product, with the noise vector, we also concatenate the actual product representation or the product embedding, and then feed it through the generator and generate orders. So these are the fake orders, and these are the real orders, which we already have in plenty. And the discriminator tries to differentiate between these two. In this conditional version of the GAN, we also add a reconstruction-based loss, which is the product component in this generated orders and the input product, just to ensure that the generated orders are restricted to that part of the space which corresponding to the input product which we gave to this network. And this reconstruction loss is back-propagated along with the traditional generated loss, and yeah, it trends in an alternative manner like any standard GAN is trained, like sometimes train the generator, sometimes train the discriminator until you get some good convergence. So once we trained this GAN, we wanted to evaluate how good they are really. Okay, and so what we did, We took some real orders which were really placed in Amazon, and we generated some orders using this generative adversarial network. And we project, these are high dimensional orders obviously. As I mentioned, that these are 264 dimensional vectors. We projected them using TSNE into a lower dimensional space, okay? And then we tried to look at 3 key aspects of this, this projection. The first projection, if you see that the real orders and the generated orders, they're really mixed well with each other, okay? So that's a good sign because the generation should really replicate the actual data. So when they're mixed well in the space, that means that we have done a reasonably good job. The generated, the actual orders in general, they come from multiple modes of the data, okay? And typically the GANs, traditionally the GANs have this problem that when the generator learns to generate samples, it ends up generating samples from 1 or 2 of the data modes. If there are 10 defined data modes, it doesn't capture all the modes while it's generating. So empirically or qualitatively at least what we saw that there are various segments which had like true real data, and when we were generating the data, we captured all of these data modes quite well when we were generating. And the final thing is when we project these generated samples and the real samples, real orders, we see that the generation is ignoring the outliers in the actual space of orders. Actual space of orders, okay? So that means that this kinds of framework can also be used to detect outliers in orders basically. Okay, we didn't do that, but that was one of the advantages of this framework. So this was all about qualitative results. I also wanted to show some, we also did some other kinds of experiments. Basically, for any new product in Amazon, we wanted to predict what are the kinds of customers who are going to buy this product and during which seasons this product will be sold. That's what we wanted to do. This is very similar to forecasting, but one thing we want to highlight in the very beginning that this method was not to compete with like the traditional forecasting methods which we use. Okay, that was not goal. That was not the goal of this work. This was sort of to just demonstrate an application of this work, because Amazon's forecasting methods will be optimized like for several years, and we won't be able to beat that. So this is just an independent experiment which we performed. So what we did for various kinds of products, we compared the generated orders with the real orders and saw how many times they match sort of. So if I look at, for example, this women party dress, and if you look at the real orders, the dark blue are the real orders, you can see that 20% of the time actually it was purchased by a male person and 80% were purchased by a female person. And our predictions said that 27% of the times it will be purchased by male and 73% it will be purchased by female. So we are pretty close to the actual distribution of orders. Similarly, unisex handkerchief, we had sort of similar distribution. Whatever the true distribution was, our predictions were quite similar. Then if you look at the seasonal demands, for example, main shorts summer collection, if you look at this product, whatever we predicted and whatever really happened, the distributions were quite close. Women winter shawl also, our predictions on the real orders, real distributions were quite close. So to summarize, we proposed an approach for plausible e-commerce order generation. We used a variation of WGAN architecture to generate plausible future orders given any new product, e-commerce product. The qualitative results look promising. I didn't go too much into the quantitative results. I would really request you to look at the archive version to look at the detailed quantitative analysis of this approach. When we submit this work in archive, it got some sort of attraction. It featured in MIT Tech Review and so on. That's all for the talk.
We have time for a couple of questions.
You mentioned the order to vec part very summarily in your presentation.
Right.
Did you do any validation of your order representation? Were you able to, for example, backtest and predict a customer's next order, or you mentioned forecasting, so at least for a set of products, were you able to predict their sales volumes?
Yes. So for order representation as a whole, we didn't do much evaluation, but for individual components, such as the product representation and the customer representation, we did quite a lot of evaluation, and they are sort of quite promising.
Sure. Thanks.
Post-start problem where you do not have enough data for users and products. And the second query is that have you tried traditional link prediction model? So essentially, user product, it basically can be represented as a bipartite network, right? So state-of-the-art advanced link prediction techniques can also be helpful in this.
Absolutely, absolutely. So yeah, to answer your first question regarding the cold start problem, so there is no issue in cold start, at least from the product part. Because we are just using the title of the product. For any product, the title is always available, so you can just feed the title and generate future orders. So that should not be a concern for the products. We can handle that. And obviously, there are various other methods for recommendation and forecasting, like the link prediction and in general collaborative filtering, and all of this works. We didn't do a very thorough comparison with those because our goal was not to really compete the state-of-the-art forecasting technique. This was more of to show that GANs can be applied to these kinds of problems, and it can give reasonable results. So that was the goal of this work.
Thank you.
And let's thank Arijit again.
Sure.
And I request
Excuse me. Hello. Excuse me. Yeah, just one question. Yeah.
Oh, sure.
So. You can connect offline. No problem.
Yeah, we can catch. Sure.
Thank you. And